going to be speaking to us first. She is she's a postdoc at Imperial College here in Ali Mashayek's group. And previously she completed her PhD in Brest in France. And I think she's going to give a bit of an intro to herself as well. So please, yeah, let's welcome Pauline.
Okay. Hi everyone. So I would like to start by thanking the organizing committee of this symposium to invite me to give a talk today. I would like to thank you all to be here today. So I am a research associate at Imperial College. I currently work with Ali Mashayek from Imperial College, but also with Alberto Naveira Garabato from the NOC, who is also going to talk today. And I also work with the Column Cofield from the University of Cambridge. So today I'm going to talk about a regional study on the energy transfers in the meso and submesoscale ranges in the ocean. So this work was a part of my PhD that I did in France at the LOPS, which is a laboratory for ocean physics and satellite remote sensing. And this work was supervised by Jonathan Gula, Pierre Penden, and Claire Menez-Gwen from the LOPS. So I will start to talk a bit about my background, to explain what led me to do the postdoc at Imperial, and to explain how the transition from the PhD to the postdoc was for me. So first, after high school, I did a bachelor in oceanography in a broad sense. So I studied a bit of everything applied to the ocean, from biology to biogeochemistry to physics. And at the end of the bachelor, I knew that my preference was physical oceanography. And after the bachelor, I decided to do a gap year to do research internship in order to see how what is the research look like from the inside. So during this year, I did 2 internships, one in France and one in Florida in the US. And after this gap year, I chose a master degree in physics of ocean and climates. And during the master degree, we have internships of a few months, and that allows us to get familiar with some topic in the physics branch. And I really enjoyed the internship I was doing, and luckily it was leading to a PhD. So I followed up my master degree with a PhD in the same university in France. I find it a bit difficult during the PhD to engage with the post-PhD life while I was doing the PhD. But I think that during the PhD, we have many opportunities to meet other researchers or to get familiar with different topics in our field. So what I did at the end of my PhD is I directly contacted researchers I had met in conferences, or I seen talks in conferences, or I just read papers that I liked. And doing that way, that might take a bit longer to set up the postdoc, because you're not directly responding to a ready-made offer, but it has as much chance to be successful. So this is how I heard about the postdoc in Imperial, and this is how I came here. So if you would like to do a postdoc after a PhD, my advice would be like not to fear directly contact researchers you would like to work with. Even if you just apply to a ready-made offer, just contact the researcher in charge to talk about the project and present yourself. So you won't work every time, that is for sure. But doing that, you just make yourself known and you have more chances to engage in projects and collaborations. So yeah, that would be my advice for academia. Just go talk to people. Okay, now let's start with science. So I will present now a bit of the context of energy transfers in the meso and submesoscale ranges in the ocean. So this is a figure of the normalized relative vorticity at the surface, and that's a snapshot in the region of the Agulhas current. And we can see that the ocean supports motions over a wide range of spatial scales.
Okay.
the scale form a continuum. So we can see that the mean circulation, which is represented by the black line with the two arrows, the mean circulation takes place in oceanic basin, which has thousands of kilometers. The largest eddy features we can see are spotted in the black squares. This is mesoscale eddies. And they have horizontal scales ranging from the Rossby deformation radius, which is about 10 kilometers at mid-latitude, to hundreds of kilometers. We can also distinguish smaller features such as eddies, fronts, and filament, and they are spotted in green. And these submesoscale currents have horizontal scales from hundreds of meters to 10 of kilometers, which marks the Rossby deformation radius. So because of the different scales, the features have different dynamics. So the mean circulation and the mesoscale eddies are balanced because of the dominating effect of rotation and stratification. And the submesoscale currents are partially balanced because of the increasing effect of inertia and vertical shear. And as we can see on this figure, because of the scale continuum between the different features, it suggests that they strongly interact with each other. So we look at scale interactions via the kinetic energy transfers, which makes the kinetic energy budget. So the scheme of the global ocean energy budget is as follows. At the planetary scale, the wind forces the upper ocean circulation. And this upper ocean circulation corresponds to large-scale mean currents, which form gyres at mid-latitude. So these gyres are represented by the white arrows on this map of mean sea surface height. And the gyres are intensified upon the western boundaries. And these intense currents are shown by the thick white arrows. So the large-scale circulation is unstable, and the mean current develop instabilities, transferring energy towards the mesoscale range in the form of mesoscale eddies. And we can see on this snapshot of sea surface height anomaly that mesoscale eddies are ubiquitous across the ocean. And mesoscale eddies amount up to 90% of the surface kinetic energy. That is why they represent a key component of the global ocean energy budget. But in the mesoscale range, the kinetic energy is transferred back towards the larger scales. This is the inverse turbulent cascade predicted by the geostrophic turbulence theory. So to reach a balance, mesoscale eddies must dissipate their energy, and some of it is dissipated locally by bottom friction and wind, among other processes. But most of the dissipation must occur at very small scales, at the dissipation scales. So that indicates that must be direct energy routes from the mesoscale downscales down to the dissipation scales. So the direct energy routes are triggered by different processes when there is a breakdown of the geostrophic balance. So it occurs via different processes for which the topographic interaction seems to play a significant role. It has been largely documented in many regions using data and numerical models that a mesoscale eddy interacting with topography can generate submesoscale eddies or turbulent wake or internal gravity waves. However, the direct energy route from the mesoscale reservoir toward the dissipation scales is complex because the balanced portion of motion in the submesoscale range can also realize an inverse turbulent cascade. So my work during my PhD focused on characterizing the variability in the meso and submesoscale ranges, which are both key ranges for the global ocean energy budget. And in the second time, we specifically focused on topographic interactions, which seems to be a significant way to channel interaction between these two ranges. So the mesoscale eddies contribute to the global ocean dynamic and the climate system via other aspects of the global ocean energy budget. So they transport on the horizontal heat and salt on a global scale. And an example of this in the Agulhas Current region, which is around here, is the Agulhas leakage. So we can see of this map of temperature at mid-depth that mesoscalides generated by the Agulhas current flowing here. So these mesoscalides transport warm water into the Atlantic Ocean. And at more local scales, mesoscalides can shape the distribution of tracers. They can steer filaments into the surrounding. On this snapshot of surface temperature, we can see a filament of cold water from the coast being advected by a mesoscale anticyclone. And such phenomenon can have impact on marine biology. So for all these reasons, the parameterization of mesoscalidae in climate model is needed and important to simulate and predict the climate variability. So if we look at this on this map of the time average eddy kinetic energy at the surface, we can see that the largest values are found upon the western boundaries. So where flows the western boundary current, denoted by the gray line, gray arrows. So this indicates that the mesoscalides are the most intense upon these regions, and this suggests the western boundaries as a hotspot of mesoscalide dynamic. In addition, the mesoscalides have been suggested to decay upon the western boundaries. So this is a map of the eddy kinetic energy fluxes divergence diagnosed from altimetry data. And we can see that there are systematic blue patterns at the western boundaries. And the blue patterns denote a net energy sink at mesoscale. So that means that mesoscalides decays in these regions. So this founded the paradigm of mesoscalide decay upon the western boundaries. And that furtherly points towards the western boundaries as a hotspot of mesoscalide dynamic. So we focused our analysis in the region of the Agulhas current. The Agulhas current is the western boundary current of the subtropical Indian Gyre. It flows along the African coast from the southern extremity of the Mozambique Channel here to the southern African tip. And from there, it retroflects eastward into the Indian Ocean. So the Agulhas current is a hotspot of variability, and especially due to the fact that it retroflects. And due to that, it's a perfect region to look at meso and submesoscale interactions. So I use a set of regional numerical simulation run with the Crowe model. And the nesting of different grids allows to progressively increase the resolution of the model. So I particularly use these two grids, that one and that one, which have an horizontal resolution of 2.5 kilometers for the largest one and of 750 meters for the smallest one. So now I will present you a study on submesoscale variability in the Agulhas inner front. So the mesoscale variability in the Agulhas current region is well documented, and it allows to define the current into two branches. The northern Agulhas current has a low mesoscale variability level, and it is stable. It is only unstable due to the generation and advection of few nata pulses a year. And the southern Agulhas current has a high mesoscale variability level, and it is unstable. Few mesoscalides are documented to be permanent or recurrent in this region. The submesoscale variability in this region has been scarcely documented, but relatively recently, submesoscale frontal eddies have been sampled by two gliders at the inner front of the current, around Port Elizabeth, which marks the transition between the two branches of the current. So we aimed to investigate the dynamic of the submesoscale frontal eddies using a numerical simulation. So first, we wanted to know if our model was simulating the same kind of submesoscale eddies which were observed. So we can see from this snapshot of relative vorticity and temperature at the surface that there is a variability at the inner front of the Agulhas current. There are several cyclones developing at the same time, and they form a vortex street along the inner front of the Agulhas current. The eddies have diameters about 10 to 20 kilometers. And if we look on the vertical section along the inner front, so along this line, we can see that the submesoscale eddies are intensified at the surface. Yes.
So how do you define eddies? How do you separate mesoscale eddies from submesoscale eddies?
So we defined eddies as time fluctuation. So we remove a time average. And we can dissociate meso from submesoscale depending on the time. So if we look at the time average on a week, it would be more submesoscale. And then we look at the diameter of the structure we see. If it's like below the Rossby deformation radius or above.
So do you have some formal filter space?
Yes.
Separate
in time mostly, yeah. And then we estimate the diameter of the eddies we see.
Okay. And what do you do with the diameter? How do you separate length scales, submesoscale, length scales?
We don't apply any spatial filter. Like we look at so the time filter allow to see time fluctuation, and if we have a coherent feature, we can like apply an algorithm to get the diameter, and we look at the diameter if it fits in the definition of submesoscale. But we don't apply any spatial filter, only temporal one. So yeah, this is the time fluctuation we noticed. And they are intensified at the surface, and they have cold water in their center compared to their edges. So to investigate the generation mechanism of the modeled submesoscale eddies, we refer to the eddy kinetic energy budget. So it is defined for time fluctuation, denoted by a prime, and the prime is defined relative to a chosen time average. So in the right-hand side of the EKE equation, there is these three terms which represent energy transfers between energy reservoir, and these three terms are indicators of instabilities of the flow. So you have instability due to the horizontal shear, to the vertical shear, and you have the bioclinic instability, which is this last term. Yes, so that's a time average of quadratic fluctuation. Yes, that's a time average of quadratic fluctuations. So we computed this. These are quantities what? Yes. Yes. So it depends on the diagnostic, but so we started to average, so we spotted an event of submesoscale eddies generation. It was a week. So we wanted like to be sure we were looking at the generation of this specific eddies. So we tried to average over a week, and then we did that for longer periods to see if it was recurrent or not. So at the longest, it was 1 year, and the shortest period was 1 week. Yeah. So we computed these three terms, and on this plot is average for specific event of mesoscale degeneration. So it's average over 1 week. So this is the three terms of energy transfer due to instability. And we see that the only source of energy for the ADs during that time is this term, which indicates the barotropic instability. So due to an unstable horizontal shear. And if we look at the vertical section of this term along the inner front, we can see that the energy transfer from the mean current towards the ADs is more intense at the surface. And that is consistent with the vertical structure of the mesoscale ADs. So this diagnostic indicates that the barotropic instability is a generation mechanism of the modeled mesoscale ADs. And we compared the energy term of the barotropic instability that we derived with our model to the one which was derived using glider data. So using the glider data, we can only compute a partial energy term. And we compare the partial energy term in the model, the partial and the full term. So this is the blue line. And this is plotted along a cross-front section, so in that direction. And we can see that the partial and the full energy term are very similar and have close magnitude. So that indicates that the partial energy term is a good approximation of barotropic instability, and that the energy is mainly extracted from the mid-current via the cross-front shear, cross-front horizontal shear. So with this study, we could complete the picture of variability in the Agulhas current region. So the northern branch has a low variability, and the variability increases downstream gradually from submesoscale to mesoscale. And from there, we wondered how do the different meso and submesoscale ADs interact with each other. So now I'm going to present you the study on interaction energy transfers between the meso and the submesoscale ranges in the Agulhas current. And we especially focus on topographic interactions. So the topographically channeled interactions are investigated using the vertical mode. The traditional vertical mode plotted here. So this is vertical profiles. They form a normal basis that describes the vertical variability of the flows. Each vertical mode represents a specific vertical structure. The barotropic mode represents homogeneous vertical structure. The first baroclining mode represents structure intensified over the first 1,000 meters, and higher baroclining mode are intensified at the surface. But we are interested in mesoscale ADs. So the mesoscale EKE reservoir is represented by the combination of the barotropic and first baroclining mode. The mesoscale EKE reservoir amounts for most of the EKE in the Agulhas current region, while the EKE reservoir of higher baroclinic mode amounts for less energy. However, the energy transfers between these two reservoirs are key for sustaining the mesoscale EKE reservoir. So we assess the mesoscale EKE sink and the contribution of topographic interaction by deriving a model EKE budget, and we derive this budget using a numerical simulation. So the model EKE budget is similar to the classic EKE budget, but it is derived in the framework of vertical mode. The classic EKE budget is the one I defined in the first study. So the left-hand side of the EKE equation accounts mainly for this term. This is the EKE fluxes divergence. And this one term equals the sum of the different EKE sources and sinks gathered in the right-hand side of the equation. So this one term can be interpreted as representing the net EKE sources or sinks resulting from the total dynamic. And the right-hand side of the equation gathers the different EKE sources and sinks. They can originate from instability processes of the current, which are these terms. They can also originate from energy transfers between the vertical mode, or they can originate from physical and numerical forcings. So the energy transfers between the different vertical modes can be done by two kinds of intermodal coupling. And the first one is the triad interaction. So these two terms. And the triad interaction can point toward the turbulent cascade or toward nonlinear interaction between eddies and the mean current. The second kind of intermodal coupling depends on stratification and topographic gradients. So these three terms point toward energy transfers between vertical modes, mainly channeled by topography. This term in particular points towards a nonlinear eddy scattering over topography. This one points toward nonlinear interaction between eddies and the mean circulation, and we interpreted this term as eddies inducing a bottom-intensified circulation over sloping bottom following Holloway in 1987. And this last term is well documented to represent the generation of internal gravity wave by eddy scattering over topography. So we performed this model EKE budget, and we specially average each term over two sub-regions of the Agulhas current, so the northern Agulhas current and the southern Agulhas current. And doing so, it allows to assess what are the main EKE sources and sinks, but mostly to relate these sources and sinks to physical processes. So the main mesoscale EKE sources are the mean circulation. The mesoscale eddies are generated by the mixed barotropic baroclinic instability in the southern ocean, in the southern Agulhas current at these two locations denoted by the red square. And this is where the Agulhas current separates from the shelf. The locally generated mesoscale eddies are straightened by eddy mean triad interaction across vertical mode. And this happened in the two subregions denoted by the hatched red areas. And such an energy transfer can also be channeled by topography at a very specific location denoted by the red triangle. So once they are generated, the eddies are then partially exported away from the northern Agulhas current and the southern Agulhas current. Mesoscale eddy also locally decays, mainly due to topographic interaction. So topographic interaction channel mesoscale eddy energy toward higher baroclinic mode, mainly in the form of internal gravity waves, which are spotted as the blue curved arrows, and more weakly in the form of eddies of higher baroclinic mode in the northern Agulhas current. The topographic interaction also channeled mesoscale eddy energy back towards the mean circulation. So the mesoscale eddy induced a bottom-intensified mean circulation over the shelf at the two locations denoted by the blue triangle. And mesoscale eddy also dissipates significantly their energy, mainly due to bottom friction in the northern region, and due to both bottom friction and the wind in the southern Agulhas current. So to sum up about the energy transfer between the vertical mode, the topographic interaction are the main sink of mesoscale EKE. The topography channels mesoscale eddy energy as much towards higher baroclinic mode as towards the mean circulation. The generation of internal gravity waves due to mesoscale eddy scattering over topography represents the main direct route, so the main route of energy dissipation towards the dissipation scale. Away from topography, the triad interactions are significant, and they denote an inverse turbulent cascade. This is represented by the red ingoing arrows here, here, and here. So to conclude on these studies, we have assessed that the Agulhas current is a generation region of mesoscalides. Mesoscalides are generated by mixed baroclinic barotropic instability of the Agulhas current, and these instabilities are modulated by the topography. Once generated, mesoscalides are partially exported mainly in the Southeast Atlantic Ocean. They locally decay mainly due to topographic interaction following three different ways, here, here, and here. And mesoscalides are also locally dissipated. And to go back on the paradigm of mesoscalide decay upon western boundaries, we show that with our model, we show that the Agulhas current region is the net region of mesoscalide generation. So that is in contrast with the paradigm based on satellite altimetry data. So we assessed that in the Agulhas current region, the local generation of mesoscalides overcomes the local decay due to topographic interaction, meaning that the paradigm of mesoscalide decay upon western boundaries is incomplete in the presence of a western boundary current. I'm done.
Thank you. Thanks, Pauline. That was a great talk. Does anyone have any questions? Colin?
What's special about the red triangle area?
It's quite special is like topography is going on there. Yeah, so here I say mesoscalides are straightened by interaction with the mean current, but that is unforced nonlinear interaction. And in this spatial location, eddies are straightened by the mean current, but this is channeled by the topography.
So is it a larger slope there?
Yes, yes. This is where the current separates from the shelf. Yeah.
I should just say, if there are any questions in the chat on the Zoom, can you put them in the chat and then we can ask Pauline them too. Pavel, did you have a question? Any more questions?
All these terms in the equations that you're thinking about linear instabilities and so forth. Suppose you were going to try to start grouping them into the most important parts. There appears, for example, that the bottom topography is tremendously important, right? And it also, when that ACC runs into the equal current, it just completely turns it around, right? So it's an amazing collision with huge shear, which is generating these eddies all over the place, right? So, thinking that there should be some kind of collective description of the type of behavior that this thing should be a generator, right? So maybe some kind of theory that involves, collective components that are actually not linear, which is maybe would be other types of. We also talk about generation controllers. This is obviously the reason of the present rich area looking. There's something more than just we look at these individual terms in our computer. We have 90 parameters. Yeah, do you have any idea what the sensitivity of these parameters is? For example.
So we didn't run any sensitivity.
Don't try. Okay. What do you think the most important question
From a simulation perspective, you mean, or from analytical?
From your viewpoint, after you've learned this is great information. You've synthesized it. You've made, you've understood a lot of the connections, and you understand the frailty of the approximations that went into them. Is there any, is there something that you would formulate as a question that you'd like to spend the next part of your life on?
So yeah, if we can dream, I would like to extend this kind of budget to other regions in the ocean, like what happens in the ocean interior, for example, in the interior of the gyres, to connect what happened like to the Mesoscaletes drifting westward. I would also like to be able to have a model solving mesoscale down to the dissipated scales and look at these energy transfers, like what's going on at small scales, because this simulation was wasn't resolving the mesoscale very well. So I would like to look at energy transfers in smaller scale ranges. That would be what I would like to do.
Well, I guess it's more of a comment than a question. So you look at kinetic energy budget and momentum equation. This is very mainstream approach. People try not to look at potential energy budgets.
Yeah.
And trace your equations. So why are you staying in the mainstream?
Because this is tricky. Available potential energy is tricky to define. So we evaluated the AD available potential energy reservoir, but not the transfers between.
That would be the most interesting part.
Yeah, that would be nice, but yeah, I think we should spend some time before how to define this, how to define the available potential energy. There are several different definitions.
Yeah.
So, but that would be nice, yes.
Lovely. Thank you. Okay, so next up we have Marilena Oltmanns, and Barsha, you've got to get the slides ready. Thank you. Do you want to wear the microphone? It's got a little Velcro. Hi, that's annoying. Also, do people think they'd be able to see the screen better with the lights off? Yeah? Good? Okay, nobody fall asleep though. Okay, well, while we're getting the slides ready, I can introduce Marilena, who is from the National Oceanography. She's a research scientist at the National Oceanography Centre in Southampton. And before that, she was a postdoc at the Helmholtz Centre for Ocean Research in Kiel. And before that, she completed a PhD at the Woods Hole MIT Joint Programme in the US. And she has very recently won a prestigious EGU award in 2021 for being an outstanding early career scientist. So we're super happy to have Marilyn here with us today. And when we have the slides ready, there we go. Perfect timing. And that's gone. Okay, all good? Lovely, thank you.
Great, thank you very much for the kind introduction. So I'm Marilena, and I work at the National Oceanography Centre in Southampton. And my research is about ice-ocean atmosphere feedbacks in the North Atlantic and Arctic regions. So we have a change of location now. And in particular, I'm investigating freshwater, which connects the ice, the ocean, and the atmosphere, because a lot of the ice that melts in the Arctic ultimately ends up in the North Atlantic as freshwater. And there it can lead to changes in the ocean and atmospheric circulations. So here you can see an example of a fresh surface layer that was obtained from mooring observations in the Oceanography Sea. So this is the subpolar region, and this shows the location of the mooring, which is a chain of instruments that has an anchor at the bottom and a floating device at the top, and then it measures a lot of ocean properties. So this was a particularly warm summer. This shows the sea surface temperature anomaly in 2010, and we have a warm surface layer. And normally, what happens from summer to winter, the water cools, it becomes denser by cooling, and then it sinks. But in this summer, it did not sink because we also had a very fresh surface layer. So this shows the absolute salinity, or the salt content in grams of salt per kilograms of fresh water. So blue means that we have less salt or more fresh water. And this by being lighter, the fresh water prevents the downward mixing. So the more fresh water we have, the colder the water needs to become in order to finally mix down. So because we don't have mooring observations everywhere in the North Atlantic, and satellite observations are not very good to measure salinity, we use this influence of the fresh water on the sea surface temperature in order to infer its variability. So I'm not going into any details, but just to briefly describe the approach. So what we do, we look at water column, and we look at the mass fluxes in and out of this water column, and we linearize the equation of state in order to obtain an equation that depends on both temperature and salinity. And then we select conditions where we have strong cold anomalies and where we can infer. So we select conditions where we can actually infer the variability of fresh water from the sea surface temperature, because the other terms in the mass budget become not important anymore. So when we do this, we obtain two main types of freshwater events in the North Atlantic, where one is driven by changes in the circulation and the other one by more freshwater inside the current system. And this is due to, for instance, runoff from Greenland, but it can also be melting sea ice. It's just that there is more freshwater inside the current, whereas the other one is a change of the currents themselves, so that more of the freshwater reaches the subpolar region. So in this talk, the first part will focus on shorter seasonal to interannual timescales and look at the influences of freshwater. The second one will be on more interannual to decadal timescales. And the third one will investigate the role of freshwater in abrupt climate change. So as I mentioned, freshwater leads to cold anomalies. And because we have more freshwater in the subpolar region, we obtain stronger cold anomalies in the subpolar region compared to the subtropics, where we have less freshwater. So the freshwater increases the south-north temperature gradient. So we always have a temperature gradient from south to north, but when we have more freshwater, this is enhanced. And this is the main energy source for extratropical cyclones, because these cyclones, they take their energy out of the background temperature gradient. And we find, so these are the two types of freshwater events that I mentioned. One is due to changes in the circulation. The other one is due to changes in the runoff melting. And these are anomalies in the winter following the freshwater event. And we focus only on this type here now, but the influences of the other one are relatively similar. So it's sufficient to just show the influences of one. So in the following, I will only show the influence of the melt or runoff driven freshwater events. So since we have this increased sea surface temperature gradient in the winter following these events, we also have an increased atmospheric instability. And this is shown in the first plot here. This is a measure of the instability. So it is enhanced in the region where we have particularly strong temperature gradients. And this happens to be the boundary between the subtropical and the subpolar gyre. So we also have the Gulf Stream there and the North Atlantic current. And this is a region where we have now very strong instability in the atmosphere. And this leads to a circulation anomaly in the atmosphere that looks like this, with a more cyclonic circulation towards the north and an anticyclonic circulation to the south. So the arrows here do not show the wind direction. They show the direction of the wind-induced current speed, because on the northern hemisphere, the flow transport resulting from the winds is to the right. So we got the convergence of the flow in the region between the two gyres, or in this region. This shows the sea level anomaly. And this is leads to a lot of smaller scale instabilities. But when we smooth over these instabilities, the net circulation induced by this atmospheric circulation in the ocean is a more anticyclonic circulation in the region where we have normally the North Atlantic current, or where we have, here's the subtropical gyre, we have the subpolar gyre here. And we have this anticyclonic circulation anomaly. So we have an enhanced eastward speed at the northern edge and a reduced eastward speed at the southern edge. So it's like a northward shift. And this ultimately also leads to a warm anomaly, because not because the water in the current is warmer, but because the current is at a more northerly location. And this happens pretty instantaneously. It's on the timescale of days. But because we have the strong cold anomaly in the first winter after the events, this response is usually better seen in the second winter after the events.
So what's the color left?
The left bottom. So this is absolute dynamic topography, but it's the same as the sea level anomaly. It's so the sea level anomaly is just it takes a different background average, but it shows the same thing. So here, if we would have taken sea level anomaly, it would have led to the same results. So when we have these big cyclones, it's not that we have, so this is an average from January through to March. So it's a 3-month average, but it's not that we have a big cyclone sitting there all the winter in theory. So in practice, it's composed of many individual cyclones. So here you can see an example of one of those cyclones, which occurred after the largest freshwater event that we recorded. And it was associated very strong wind speed. So this is Greenland here. This shows the wind speed. And it was also associated with a lot of cold air advection over the US, leading to minus 20 degrees centigrade and above air temperature over the North Pole, and a lot of flooding events over the UK, because this is in the pathway of the strong winds. And those events, they can cause a lot of destruction, but so we cannot say that they are due to the freshwater, but the freshwater leads to conditions that are favorable for storms to develop by increasing the atmospheric instability. In summer, the situation is a little different. We still obtain stronger temperature gradients associated with either the cold anomaly or this northward shift of the ocean currents. But we also have a strong temperature gradient across the coast because the land heats up faster. So in summer, the land is always warmer than the ocean. So we have the anticyclonic circulation anomaly is rotated over the continent. And depending on where we have the strongest temperature gradient, the jet stream indicated by the big arrows here is also shifted, and it meanders northward around Europe instead of crossing it. So then we get warm and dry anomalies over Europe. So these are now averages from May to August over 4 months, and this shows the temperature anomaly over Europe, and this is precipitation minus evaporation. So after stronger freshwater events, we also obtain warmer and drier summers typically in Europe. But the location of these anomalies is highly sensitive to where we have the temperature gradient over the ocean. So now a quick summary of this first part. The freshwater leads to enhanced cold anomalies with sharper sea surface temperature gradients, which destabilize the atmosphere, and the response leads to shift in the ocean currents. And in subsequent summers, the jet stream meanders northward following the SST fronts, and this leads to warmer and drier weather in Europe. So now on longer time scales, what does freshwater do? Well, to answer this question, it's actually more instructive to look at what happens when we don't have strong freshwater events. So we again use an index which is based on the large-scale atmospheric circulation in summer to distinguish between the two types of freshwater events. But we now look at times when we do not have a strong freshwater event, but in the time in between when we don't have strong freshwater events, and we construct a composite. So when we don't have strong freshwater events, we obtain warm anomalies in the North Atlantic. No surprise, because there is less freshwater. And earlier studies have shown, one can also do a heat and mass budget to show that this warm anomaly is driven by a buoyancy-driven northward surface flow. So the ocean actually loses more heat. This shows the heat fluxes. The ocean loses more heat in this region because it is warmer. So it is not that the atmosphere drives the anomaly in the sea surface temperature or warms the ocean, but it's the other way around. The ocean loses more heat and it becomes denser and sinks, and this draws in more water from the south to the north, maintaining the warm anomaly. So it's a very stable circulation. However, we are interested now in how stable is it actually? Can it stop, or how does it evolve? So what we do is we define an SST mode, a sea surface temperature mode, based on this pattern, and we investigate how it evolves. So this is our SST mode. We can call it warm anomaly mode or buoyancy driven mode based on earlier studies. And we investigate the time variability of it. So this is shown here. Let's call it R of t is the time variability of this SST mode over the last 70 years. And we want to know how does it start and how does it evolve. So we take the time derivative, we take the time derivative of this time series, and we regress the sea surface temperature on the result. So then we obtain a new mode that earlier studies have referred to as wind-driven mode because it's associated with north-south shifts in the Gulf Stream or North Atlantic current here. When we have a northward shift, it's a warm anomaly. When we have a southward shift, it's a cold anomaly. And we call it just transition pattern. So this pattern transitions into this pattern. And we want to take it one step further. We take the time derivative once more. So this is the time variability of this SST mode. But we take now the time derivative again to see what is the pattern that leads into this pattern. So when we do this, we obtain the original pattern back, but in the opposite phase. So in other words, the two patterns, they form a cycle. If we decompose the sea surface temperature field into these two different modes and some residual, then we can solve the differential equation. So this is the time variability of the first mode. This is the time variability of the other one. And one is the derivative of the first and the other is the negative derivative of that. We can solve this and we just obtain sines and cosines. So this cycle is a really important cycle in the North Atlantic. It explains over 50% of the sea surface temperature variability, and it's most pronounced on decadal timescales. And because the sea surface temperature is so important in driving the large scale atmosphere, it also explains a large part of the atmospheric variability. So it's actually not only an important cycle for the North Atlantic, but also for the Arctic. The Arctic Ocean, however, is special because it can have two different circulation regimes, where one is more cyclonic and the other one is more anticyclonic. And in the more anticyclonic regime, fresh water is accumulated in the Arctic, and in the more cyclonic regime, which is driven by the more cyclonic winds, it is released and can be exported to the North Atlantic. So we find that this buoyancy-driven mode that I showed you in the beginning is associated with a more cyclonic circulation and leads to an enhanced ice export, but not yet import into the North Atlantic, but the ice accumulates. This shows the ice concentration along the eastern coast of Greenland. So this is a regression again in winter. But as this mode transitions into the negative transition pattern, the ice anomaly propagates, then it is released. So as the sea surface salinity. This is blue means again we have more fresh water, so fresh water is released in the subpolar region, and this leads to a cold anomaly. So we have this cold anomaly. We are now in the opposite phase of the buoyancy-driven mode. Then this phase again leads to a series of feedbacks in the atmosphere and in the ocean that ultimately bring us back to the warm anomaly mode that we had in the beginning, since we have this cycle. So this is just the cycle I showed you in the beginning with the atmospheric feedbacks added. But rather than going into the different feedbacks, even though they are very exciting, I would like to focus on the stability of the cycle as a whole. So how strong are the individual dynamical links relative to stochastic variability? Or can we also go backwards sometimes or take alternative routes? And in order to answer this question, also how does this cycle change over time? And in order to answer this question, we first transition to polar coordinates because we have a cycle and we have these two orthogonal SST modes. So we just transform them into a radius that shows how strong the cycle is at any given time, and an angle that shows where in the cycle we are at any given time. So here you can see a polar histogram. So this was our warm anomaly, and it transitions into the negative transition pattern. So this is a cycle, and the length of the bars here shows how frequent each mode is, and the color shows how strong it is. So in other words, the warm anomaly is the most frequent mode, but it is not particularly strong. And also the feedbacks associated with it are not particularly strong. So it's the weakest link in this in the chain, the one that takes most of the time. And this is a problem because this is the mode that should lead to a more cyclonic Arctic gyre and ultimately bring us into the next freshwater event. But this is not what always happens. So when we look at this in more detail at this mode, we see from SST-forced model simulations and also from observations that we have a more anticyclonic circulation. So this is shown by the arrows in the North Atlantic region, but a more cyclonic circulation over the Arctic. But compared to the other feedbacks, this is the weakest signal. So we have a more cyclonic circulation over the Arctic, but it's so weak. It takes a lot of reinforcing feedbacks between the ocean and the atmosphere, and a lot of time for this feedback to become strong enough to have an Arctic freshwater release. And this is not what always happens. In recent years, in particular, this anticyclonic circulation anomaly is also associated with more runoff and melting. And this is, leads to more freshwater inside the current system. And we already obtained cold anomalies without triggering the switch in the Arctic gyre. So the water is already fresh enough to lead to cold anomalies, and it is not needed. The Arctic freshwater release is not needed to continue with the cycle, because even though the cold anomalies look different, they trigger the same feedback mechanism. So the cycle just continues with it. In other words, so this is again the mode here we obtain is the same mode that we use to distinguish between the two types of freshwater events. So what happens is that we take a shortcut. And when we have a warm anomaly, we get directly to the next cold anomaly without this switch in the Arctic gyre. So we get a cycle that is much faster now. And this has two important implications, one for the North Atlantic and one for the Arctic. So first, the one for the North Atlantic. For the North Atlantic, we obtain a faster variability and a switch of the decadal timescales to interannual timescales. So this is a wavelet. The color shows the power. Here you can see the time, and this shows the periodicity. So this is for an atmospheric mode. It doesn't really matter which one we choose as long as it is part of the cycle. So the first plot shows an atmospheric mode. The second one is the warm anomaly mode in the sea surface temperature. And we always have an enhanced variability when we have the cold anomaly. But over recent years, this increased. And here we have a constant high variability, even though we were transitioning between warm and cold anomalies all the time, which you can see here. So this was the decadal cycle that I showed you earlier with the derivatives, but it's now actually on intraannual timescales because we skip the step that takes most of the time. We skip the Arctic freshwater release. In the Arctic, so again, this is all based on observations. So in the Arctic, we have the Arctic oscillation is, so this is described by the Arctic Ocean Oscillation Index. This has now been in an anticyclonic regime for over 20 years because we did not have the switch to a more cyclonic Arctic gyre. And this predominantly anticyclonic regime has led to a large accumulation of freshwater in the Arctic that is observed by many observational campaigns. So there's actually a large concern now that this freshwater could be released because it's a huge reservoir that is observed. And knowing that already small variations in freshwater can have a large impact on the North Atlantic climate, there is a concern that this freshwater could.
So you say that the Arctic gyre is anticyclonic. Is it globally anticyclonic for the whole Arctic or only over the Beaufort?
Oh, for the Beaufort gyre. But this is the
Locally.
Yeah, but this is forms the largest part of the Arctic gyre. It's the most dominant mode of the Arctic gyre. Yeah. And it's what I should also say, it's always the anomaly. So it's not the absolute circulation. And so just to summarize the second part, these regular Arctic freshwater experts in the past have formed a really important part of the North Atlantic climate variability and has led to a decadal scale variability. But over recent years in particular, the climate has become so warm that we have more runoff and more wet melting. And this has interfered with this natural circulation-driven freshwater cycle. And this has prevented the Arctic freshwater to be released. And instead, it has led to an increase in variability in the North Atlantic region and a reduction of variability in the Arctic and an accumulation of freshwater in the Arctic. So the last part is, can amplified Arctic warming tip the North Atlantic freshwater cycle? It's more specifically here, what is the chance of having an Arctic freshwater release and what would happen when it is released? So because we can, from the observations that we have in the Arctic, we know that if we have an Arctic freshwater release, it can lead to an at least temporary shutdown of ocean convection. But we don't know how likely this is. But why should we actually care? Well, when we look at paleoclimate studies, they have revealed rapid temperature changes of up to 10 degrees within a few years to decades in the climate system. And these have been linked to freshwater releases into the North Atlantic. And the possibility of freshwater related tipping points, so this is a rapid transition between different equilibrium states of the climate system, is also supported by a range of models. However, not by current IPCC models. It's supported by more idealized, also more complex models, but current IPCC models do not actually resolve freshwater very well. And we also currently witness the fastest Arctic sea ice decline and the largest freshening in at least 120 years. So it is a concern in both the Arctic and the oceanography community, and it's good to investigate this. So interestingly, we observe that when we have these runoff or melt-driven freshwater events, we have this northward shift of the North Atlantic current, and this shift leads to an SST pattern that is not equal to the buoyancy-driven SST pattern, but it is very similar in that it also has a sea surface temperature gradient that is enhanced from the subtropical North Atlantic towards the Arctic, and so it leads to very similar responses. And here we have a sea level pressure anomaly. So this is a more cyclonic anomaly or less anticyclonic circulation anomaly after these runoff or melt-driven freshwater events. And we also see a more cyclonic circulation in the Arctic. So actually, after the strong recent freshwater events, we almost had a switch of the Arctic circulation. And it was for the first time in over 20 years, the atmospheric circulation actually became cyclonic, but it was not long enough to trigger a switch. So the Arctic Ocean recovered, and we didn't have these release. And since then, we did not have such strong cold anomalies. But can it happen in future? Well, we have a freshening trend also. This is a linear trend over a 70-year period. And we have this trend as particular in the eastern subpolar region, because in the western subpolar region, it's still, the heat fluxes are still strong enough to mix the freshwater down relatively early in winter. And this leads to this cooling trend. So in the long term, we expect that the melt-driven or runoff-driven freshwater events will become stronger. So they trigger also stronger temperature gradients, stronger feedbacks, and they can eventually potentially lead to an Arctic freshwater release. At least the Arctic community believes it's just a question of time. I'm unsure about this, but it's definitely an exciting time. So we don't know what will happen. So another risk is that when we look at mooring or Argo observations in the subpolar region, so this is here in the Labrador Sea, this is the region where we have deep convection, and this is one of the most important regions for the export of freshwater. We see that there's a very strong seasonal cycle. So we have warming in the summer and then freshening, which mostly occurs from summer to autumn. But then in winter, the freshwater is mixed down. So this is a time series and this is depth. And a lot of the freshwater is then, when it cools in winter, it is mixed down. But because we have now more freshening, we get a stronger seasonal freshwater cycle. And the time that we have to mix the freshwater down is getting smaller, because it takes longer in order to break or erode the fresh surface layer. And also the new freshwater in the spring comes earlier now. So this is another critical threshold potentially, because when it stays at the surface, it can prevent deep convection also in the subsequent years. So there is a nonlinear effect that freshwater can accumulate, but it hasn't happened yet. So there are a lot of open questions, but there are a lot, we don't really know. And the problem with that is also that climate models have large freshwater biases. So this is an example just of a reanalysis model, which even assimilated the freshwater. So it knew that, so it's a comparison with Argo flows, and it assimilated the Argo flow observation. So it knew that the freshwater was there, but it was so inconsistent with the rest of the model parameters that it still reproduced very large errors in the sea surface salinity. And many global climate models in the subpolar region, including the CMAP5 and CMAP6 models, have freshwater biases of about 1 gram per kilogram in the subpolar region. So for context, this is an error that is 1 order of magnitude larger than the accuracy that would be required to predict something like the hottest and the difference between the hottest and the coldest, or the wettest and the driest summer. So really tiny variations in freshwater are important, but are currently not captured well in models. But I do not want to end too pessimistically, so I think it's a good time to stop here and say just that freshwater is a really important driver of the North Atlantic and Arctic climate variability. There's some people say there is an increasing chance now of having a very large Arctic freshwater release due to the feedbacks to melt and runoff-driven freshwater events, but climate models do not capture this. So we don't really know what will happen. Thank you.
That was great. Do we have any questions?
Yes. Do you know if people attempted to take decent global coupled models and just flush fresh water in the North Atlantic and see what it tips over the climate?
Yeah, those are called hosing experiments, and they have been done with different results. So some models, some idealized models that are not that complex, they observe then a shutdown of the overturning circulation, which has some implications, but other models don't. And there are a lot of uncertainties, a lot of disagreements between different models. And also, we don't really know if this is such a big problem if we have a shutdown of the overturning circulation, because global warming in the Northern Hemisphere is typically a larger signal than the temperature change we get in the subpolar region that would result from a shutdown in the overturning circulation. So in the Northern Hemisphere, our climate is more strongly influenced by what direction the wind comes from. So when we have just the colder subpolar region and the westerly winds advect the temperature anomaly over the continent, then one can observe, okay, if there is a 2-degree temperature change in the subpolar region, there's also a temperature change over Europe, but this is relatively small and hard to measure compared to for instance, the global warming signal. However, if we have a strong temperature gradient, if this shutdown leads to a stronger temperature gradient and the winds suddenly come from a different direction, then we have 20-degree temperature changes, depending on whether the winds come from the north or from the south. And the models also disagree in these responses. So it's really difficult to say what will happen if we have large freshwater release.
So to speak, the models are too bad.
Currently, yes. Yes, but I know there's a lot of research done to improve the representation, especially in the subpolar region, because it's one of the most poorly represented regions in the global climate system. It's also a really complicated region, especially for freshwater, because it depends on so many different factors like the Arctic sea ice thickness and the small-scale eddies that advect freshwater from the boundary currents into the interior. They require very high resolution because at the Northern Hemisphere, the Rossby radius, which is a really, really important quantity for the dynamics, the further north you go, the smaller the Rossby radius becomes. And this needs to be resolved by models in order to resolve the dynamics. And now it's mostly parametrized because it requires too high of a resolution.
So I was wondering, currently, my understanding is that a substantial part of the Greenland glacier melting comes from ocean heat transfer. But the Greenland glaciers are retreating on land, some of them. So we haven't decades to expect that cycle to be disrupted by that.
So I think the last studies I followed with that are still a little bit too old, but it was about 50%, 50%. So 50% was terminating glaciers driven by ocean warming and internal glacier dynamics, and 50% was driven by surface warming. So, and I think actually the surface warming has increased over recent decades, but I don't know the newest studies about this.
Any more questions?
Long-term climate change is just going to simplify the problem here.
Maybe. Yeah.
There's something positive.
Okay.
That's a really optimistic note there. Lovely. Well, if there are any more questions, let's thank you. Now we will have just a quick 10-minute break. Stay back in here for the first class.
I might actually use this stick.
Yeah.
Yeah, no, that's the... Yes, wake up, Ali.
Should we change the camera angle so that you can be seen over here?
Yeah, I might.
Yeah.
So hard.
We got shown how to do it earlier. Wait.
We can't
I don't know. Oh, look, see. Oh, now it's gone from here.
Oh.
Oh.
Okay.
Where's that? How do we make this screen again?
So, do they see the slides at the moment?
Yeah. They can see the slides.
If they see the slides and I can flip the slides, it's probably okay. Unless, yeah, Barsha might not.
Oh, wait, maybe.
We didn't want the other way. These ones change the
Thank you.
Okay, so our first speaker is Alberto Garabato from the National Oceanography Centre and the University of Southampton. And Alberto has a wealth of experience in physical oceanography, in particular observational oceanography. So he's here to tell us about the real ocean. As our previous speakers have, to do that. Alberto did his PhD at the University of Liverpool and has held academic positions at the University of East Anglia and the University of Southampton. And we're really happy to have him with us speaking today. So I will hand it over.
Thank you very much, Lois. Yeah, thank you. Thank you all for inviting me to talk to you here today. So unlike the previous two talks that were beautiful and polished and all the work made sense, I thought it would be interesting to give you an impression of what research underway is like by telling you about an experiment that we are currently doing in the North Atlantic to try and deconstruct or understand the way in which deep ocean upwelling works. And this cartoon here kind of summarizes the two contrasting paradigms that are at play here. So one of the ideas is that deep ocean upwelling is primarily driven by centimeter scale turbulence linked to the breaking of internal waves in the interior of the ocean. And the newer view suggests that much of the upwelling happens in thin bottom boundary layers linked to a process associated with those bottom boundary layer processes. So BLT is the name of an experiment. So there was an iconic paper in the 60s by Oltmanns in which he set out this view of how deep ocean upwelling works, called abyssal recipes. Here we designed an experiment which we christened bottom boundary layer turbulence recipes to have some sort of, play some sort of joke on Walter's paper. And I should also say that this is by no means, I have a small contribution that I've made to this work. This is the work of a big team of people from various institutions in the UK and the US. And as I say, the caveat of this work is that it's underway. So you will see things that are barely hanging together coming up. But in any case, let me introduce the problem to you. So as I just mentioned in response to Pavel's question, this field was started by Oltmanns, that gentleman, in the 1960s. When he had this bright idea, he was thinking about how the cold, dense waters that sink to the bottom of the ocean in certain areas of the polar regions come back to the surface across the ocean's mean density structure. So this is the kind of cartoon of the thermohaline circulation that you might have seen before. The blue arrows indicate cold waters sinking and expanding along the deep ocean. And then at some point, those waters get turned into warmer waters. This upwelling doesn't go all the way to the surface. It comes up to more or less halfway. So we're talking about the bottom part of the ocean, not the whole water column. And those warmer waters then eventually make it back to the regions where they first sank. So in this way, you close this global thermohaline loop. And what Walter was thinking about is summarized by this picture here. So this is a section of density across the ocean from observations. The Southern Ocean is here. This is Antarctica. That's north. So this could be, this is the North Pacific, but it could be the Atlantic. It wouldn't look too different. And basically, we know from observations that these dark green waters at the bottom of the ocean sink here near Antarctica and also in the North Atlantic. So Walter was thinking about the following problem. If the ocean is stratified, so this is density increasing towards the bottom of the ocean, the contours refer to density surfaces, all the way to the bottom, then this water sinking here at some point must be transformed into lighter and lighter and lighter waters if the ocean is to remain in a steady state. And thinking about this problem, he proposed that the process that enables those waters to cross the ocean's mean density structure must be associated with something very counterintuitive, which is centimeter scale turbulence in the ocean. So the flows in the ocean are the smallest scale at which the ocean moves. And so he reasoned that by applying some mechanical turbulence to this water column, you could mix these denser waters with lighter waters above, and in that way you could enable the dense waters to become lighter and progress across that mean density structure. Now, in the following 3 decades, I'm going through this field very quickly. I think we built a picture of how this centimeter scale turbulence in the ocean happens. And that picture is attempted to be summarized here by these 2 panels. So the panel on the left is a fairly iconic figure from Kurt Paulson's work in the 90s. So this team of people conducted the first deep ocean measurements of centimeter scale turbulence by deploying specialized turbulence profilers from ships. And this is in the Brazil basin, but if you look at many other regions of the ocean, it looks similar to this. So what you can see right away here is that, well, the colors indicate the strength of the diapinal diffusivity. So this is the rate at which centimeter scale turbulence mixes the ocean in the vertical. And you can see that that's enhanced by an order of magnitude of more over the rough topography of the mid-Atlantic ridge here. Now, if you look at the panel on the right-hand side, this is a compilation of this type of data from lots of different campaigns in the deep ocean, and the same quantity is plotted here, but now it's a full depth average. And basically what you can see is that the intensity of the mixing rate tends to be enhanced in regions where there is complex topography, and it's smaller in regions away from that complex topography. And I should have said that the number that we're aiming for, the number that oceanographers are trying to find in the ocean to try and sustain deep ocean upwelling in the way that Oltmanns suggested, is something on the order of 10 to the minus 4 meters squared per second. So it will be about 1 or so in this scale. So it's 10 to the minus 4 here. So that's the kind of global mean deep ocean turbulence that we're looking for. But there is a problem with this picture. One of the features that you notice here is that the mixing is intensified over rough topography, but it's also generally intensified towards the bottom of the ocean. And that's going to have certain implications for the role of turbulence in sustaining deep ocean upwelling. So in the last few years, people have studied these implications and thought about what they mean. And I think you can quickly see or follow the argument by simply considering this equation here. So this is the buoyancy budget of a deep ocean water parcel. So imagine that we have a water parcel in the deep ocean. We follow how its buoyancy changes as it moves along. So the term on the left-hand side here shows the rate of change of the buoyancy of that water parcel that circulates around the deep ocean. And that has to be balanced by the divergence of something that we call JB, which is the turbulent buoyancy flux. So it's the buoyancy flux associated with this really small scale motions in the ocean, steering the edges of that water parcel and mixing it with its surroundings. That buoyancy flux is proportional to the diffusivity that we introduced earlier times the gradient in buoyancy. So what various authors have suggested is that if you think about this equation and you think about the typical distribution that we found from measurements of the intensity of turbulence, so remember that turbulence intensifies with depth, typically in the ocean, then if you have a water parcel here, such as this gray box, and turbulence intensifies downward, if you're mixing that box more intensively with the water below than with the water above, then on average, the water parcel will tend to get denser, not lighter. So the turbulence that we've observed, it would appear to induce diapinal downwelling across density surfaces rather than upwelling. So we have a problem. So the only place where this might not happen is when you get very close to the topography, to the bottom boundary. You cannot mix across the solid earth. So if you follow that reasoning, then this water parcel that is sitting right above the bottom can only mix with the water above and it would upwell. So based on this simple argument, these various authors suggested that perhaps much of the upwelling in the deep ocean happens right next to the boundaries, in bottom boundary layers. And you can estimate the velocity across those density surfaces, the diapinal velocity, as being proportional to the divergence of the turbulent buoyancy flux divided by the gradient in the buoyancy. Okay, so that's the premise. That's what I just said. So the cartoon that is coming out of this proposition, which at this point is just theory, is that perhaps the turbulence in the interior of the ocean does downwelling instead of upwelling, and we have a lot of upwelling focused along the bottom here, along sloping boundaries. So it's a very different view of the ocean.
Can I ask a question?
Of course you can.
Can you go back one slide? So that one that's sinking, right? So the parcel below it is
Yes.
negative and that's there sink. And so the whole water column in that one framework is sinking. And you have higher buoyancy at the surface. So you have mixing, and through that you are re-stratifying, increasing the stratification. And that can't be, right?
That can be. I mean, I guess in your cartoon, yeah, there's no horizontal dimension, which would, horizontal motions would rapidly tend to homogenize that anomaly in stratification. But yes, there's clearly a problem. I'm not suggesting that this is what happens. This is the very simple theoretical idea that motivated a revision of Walter's view, and it's not really fair to blame Walter for this, because he never said that upwelling was focused in the interior of the ocean. That's just the way that the community took it. It's that sort of thing when you read an old paper and then you do something, and then the next person doesn't read the old paper, they read your paper, and it's kind of Chinese whispers, through the decades. And at some point the detail gets lost and people start thinking that Walter said this, and you go to that paper and say, he never said that. But anyway. Yes, Pavel.
So you're talking about microscale mixing, right?
Yes, microscale.
What about breaking waves in this picture?
Yeah, so the breaking waves would be part of the microscale mixing. So I'm talking about, yeah, little parcels of different density mixing with each other at the molecular level, and the turbulence folds the buoyancy contour so that they can do that most effectively. Yeah. Okay. Oh, sorry.
How can you get downwelling if you have turbulence mixing within the lift up?
So if you think about just this little parcel here, so you're mixing it with the water above and with the water below, but observation suggests that the mixing with the water below is stronger, simply because turbulence intensifies downward. So just thinking about this isolated water parcel, this would tend to be made denser rather than lighter.
So the deep JD has the wrong sign.
Does it have the wrong sign? Yes, yes, this has the unexpected sign. So it's giving you unless I got the signs wrong in this equation, because this is all on the way. This should be negative. It's pointing downward in this case, and it's pointing upward in that case. Should be. Does that make sense? Maybe. Okay. In any case, this served as an excuse to do a new experiment. And the new experiment is called BLT, but before I do that, okay, so that's the idea of the bottom boundary layer turbulence, perhaps focusing a lot of the deep ocean upwelling. But there are several problems. Even if you believe that that's happening, there are several problems. So this is one of the representations of that bottom focus process happening. This is from work by Raffaele Ferrari and colleagues a few years ago. And in the usual theoretical approach, they really simplify the ocean into 3 layers: an interior, some sort of transition layer that has some stratification, and then a bottom boundary layer that has very weak stratification. And they argue that if we want to have upwelling next to the boundary, then if you think about the turbulent buoyancy flux, which is what's shown here as a function of height, well, we know from observations that that's increasing downward. But at some point, that needs to go to 0 at the bottom over some vertical scale. Now, it's customary for the oceanographic community to express the turbulent buoyancy flux as the product of the rate of turbulent kinetic energy dissipation, which is one of the things that you actually measure with your profilers, and a mixing efficiency denoted here as gamma. And there's an extensive literature on what the value of that that gamma is not a constant. It depends on all sorts of flow properties. We're not going to really get into that, but the argument here is that in order for this to happen close to the boundary, perhaps there's some interesting physics hidden by gamma and the way it changes towards the bottom. And those physics, we really don't know what they are at this point. Okay, so this is the experiment. So this is underway. We thought, okay, let's test this idea by going to a small ocean basin that is manageable. It's not too far. It's shallow enough that we can measure frequently, comparatively frequently, and it's deep enough that it's still a deep ocean, and it has decent tides, because tides provide one of the main sources of mechanical energy for ocean turbulence. And basically, this is what we chose. We chose the Rockall Trough, which is here to the west of Ireland, and we set out to measure the net mixing and upwelling in this basin, and also the contributions from the boundary and the interior of the basin. And the way in which we are trying to do that is through 3 research cruises, 2 of which have already happened. The other one is happening in July, August. And there are various activities that we're going to do there. We're going to inject dyes and tracers in the bottom boundary to see how they spread. And hopefully that will tell us something about upwelling and mixing. We're going to measure turbulence in the water column through the profilers I mentioned earlier. And we're also going to deploy some moorings next to the bottom, in which we're going to try and measure the turbulent buoyancy flux directly and see how it changes with height, to see whether that cartoon in the previous slide has any value. So last summer, we went to the Rockall Trough, and this is on the eastern flank. This is actually measurements of topography from the ship. And we went to a canyon on the continental slope on the eastern side of the trough. So you can see the canyon here. We chose a canyon because we wanted somewhere where we thought there would be some turbulence, a signal, something happening. We didn't want to go to a totally boring region. And we did a bunch of things there. So we injected dyes and tracers, as I said earlier. We deployed moorings like the ones that Marilena was mentioning earlier, but these ones focused at the bottom. So lots of instruments next to the bottom. That's to measure the turbulent buoyancy flux. And we also deployed lots of instruments from the ship. And I'm going to tell you about some of these measurements now. Okay, so here's a different view of the canyon. I think that used to be the other way around, but never mind. You can get it. Yes, if you just tilt your heads this is the canyon here. So the black lines show topography, and the various labels indicate various things that we did in the canyon for a couple of weeks. So the whole campaign was 6 weeks, but this is just showing you measurements for a couple of weeks. And the first thing that I'll show you, so one of the things that we did is we injected a dye fluorescein about 5 meters above the topographic bottom, and this was at a depth of 1800 meters in the canyon. And then we watched how it spread for several days. One of the things that we measured right away is that there seemed to be a mean up canyon flow of something like a couple of centimeters per second. That seemed to be, regardless of how you measured it, you seem to get this consistent time mean up canyon flow of a couple of centimeters per second. So by time mean, I mean average over at least one tidal cycle. And this is how we sample the dye. So first we injected the dye. And you know how you inject dyes in your numerical simulations? Maybe you've seen this before, and you have a perfect point source, and it just spreads and it looks beautiful and so on. This was anything but elegant. I don't have any pictures with me, but basically the whole deck of the ship was covered in green. The scientists were covered in green for several days. They were washing, and it wasn't coming off. The whole surface of the ocean around the ship was green, but somehow, some dye got to the bottom, and we watched it spread. And of course, once you put the dye in the bottom, you have a problem. You need to measure it. You need to know where it goes. So the way, and we need to drive the ship around, responding to where we find it. So the way we set this up is we define this sort of grid with letters and numbers. And we basically played battleships with the dye. So the dye was being affected by the tide, swinging from one side to another. At the same time, there were other flows that were taking it up the canyon. We were trying to find it all the time, turning the ship around, calling the bridge, go that way, go the other way, go. Well, anyway, it was fun for a couple of days. The way in which we sample the dye was through this instrument called the FACITV, which you can see here. So there's a boom here with a winch, and this instrument is hanging from it. And basically, the special thing about this profiler is that it profiles very quickly.
So did you sample each?
No, this was just a way to communicate with the person driving the ship about where to go next, depending on the latest measurement. So it was a sort of real life. There was no strategy. The strategy was let's react to what the dye is doing, and this was the way to communicate. And the unique thing about this instrument is that it's ultra fast, which basically means that it profiles vertically at 3 meters per second, which is very rapid compared to most other profilers. And you can find various things about the instrument there. Anyway, that obtains some measurements of the dye. And you can see those measurements here. So this is time along the x-axis. So this is the hour of day. This is depth from 1400 meters to 1900. At the top, you see temperature. And at the bottom, you see dye concentration. So dark green indicates a lot of dye. And the whitish green indicates very little dye. And okay, you probably think, how can he do anything with that, right? But just look at this. When at the start of the experiment over here, there was a lot of dye in this sort of green, light yellow water. And by the end of the experiment over here, this is a couple of days later, there was now some dye in this sort of orange water. So the dye seemed to be spreading towards warmer water. I mean, it was spreading anyway across all sorts of directions. But we seem to be finding more and more dye in the warmer water. So it's not very clear from this perspective, but when you plot it in temperature salinity space, you can see a little bit more. So these diagrams here, some of which I'm missing labels and whatever, but this is basically temperature on the y-axis, 4 degrees, 5 degrees, and this is salinity along the x-axis. And this is hours since release of the dye. So 2 hours after release, almost all of the dye was located at one point, water with a particular temperature and salinity. But as time goes by, you can see that the dye is spreading gradually in that sort of diagonal upward direction towards warmer and saltier water. And very little dye spreads towards colder and fresher water simply because it can't. There's a topographic boundary below. But from there to there, you can see that the dye has spread towards that warmer water. So there seems to have been a net upwelling across temperature and salinity contours or density contours of the dye. And we can use these measurements to estimate the rate of diapycnal upwelling. So when we do that, so the dye warmed by about 0.2 degrees centigrade per day. And if we use the mean temperature distribution in the canyon, then we can translate that to meters per second. So when you do that, you get a diapycnal velocity of something like 100 meters per day. This might not tell you much, but this is 10,000 times the global mean number that you need to close the overturning in Walter's way. So it's basically very, very rapid upwelling happening along this canyon. We contrasted this dye-derived number with the up canyon, the mean up canyon flow that we measured directly from current meter instrumentation, which was 2 centimeters per second. So if you take that 2 centimeters per second and you multiply it by the mean topographic slope of the canyon, you get something that is of the same order of magnitude as the dye-derived number. So we are, even though this is preliminary, we're pretty sure that the order of magnitude is going to be right. But then you can, this is recorded, so I may regret that. Okay, so one other interesting thing that we observed. So this is from a mooring that we deployed here at the base of the canyon. So this is towards offshore from the place where we injected the dye. And if you focus on the bottom panel, which measures dye concentration as a function of height above bottom, you can see that a few days after the dye release, we observed this column of high dye concentration extending over a couple of 100 meters at least, which might be telling us that some of the dye is now being exported towards the interior of the basin. Okay, so remember that this is where we started from. And I think we have found on the basis of this one experiment that this part of the cartoon, in terms of there being rapid upwelling, seems to hold. So we're now going to try and figure out what happens in this bottom boundary layer. What are the physics that driving this upwelling? And in order to do that, one of the things that we did, that's again turned on its head. I'm not sure why, but anyway, we went to another location in the canyon. And one of the things that we did was to sit there with a ship for a tidal cycle for 12 hours and measure very quickly the changes in the temperature and the salinity of the water, and also the changes in the turbulence. So just a sample from that kind of survey is shown here. So this is time along the x-axis. This is 6 hours. The labels have gone because of the transfer to different computer, but they were there. And depth is along the y-axis in both plots. Again, there used to be labels here. The top panel shows temperature, which, this is the first kind of striking thing that you see. There's this sort of sine wave happening here, which is happening at a tidal period. So that seems to be an internal tide, an internal wave in the ocean with a tidal periodicity that is making water parcels oscillate in the vertical by a couple of 100 meters. And if you look at the bottom panel, which is shows the rate of thermal variance dissipation, so this is the rate at which temperature is mixing at centimeter scales, then what you can see is that as the tide enters this phase over here, so where you develop this very homogeneous body of water here, the turbulence intensifies by, you can't see because the labels are gone, but by a couple of orders of magnitude. And then as you recover stratification over here, the turbulence gets more confined to the bottom and eventually vanishes. So there seems to be a process happening here, extending over a couple of 100 meters in the vertical, linked to weak stratification that is sustaining the turbulence. Now, we are still investigating what that process is, but I think we can see a few clues that what's happening here is not shear-driven mixing, but convection. So you might just about see the magenta contours over here. Those show regions of negative vertical stratification. So where you have cold water overlying warm water and not the other way around. So this is the way that the ocean doesn't like being. And at the leading edge of that, you see this very intense mixing here. And you know, these two patterns basically match rather well. And just to show you that, you know, we're not talking about a small feature, just to put these things into context, this sort of feature is almost as high as the Tour Eiffel. So, you know, it is, you can imagine this big skyscraper overturning and convecting and mixing is going to be a big thing. And yeah, I mentioned that. Okay, so I just postulated, I guess, that a lot of that mixing is linked to convection. And I did that on the basis of having this couple of hours where there is sustained and stable vertical stratification. So just to show you that there's a little bit more to it than that, what we did here, this is based on a mooring deployed in the canyon. We have depth on the y-axis and time on the x-axis. What's shown here is the up canyon velocity. So you can see the tide, you can see the flow going up and down the canyon. But you can also see that close to the bottom, the amplitude of those velocity fluctuations decays. And if you do an average of the tidal ellipse as a function of depth, you get this sort of shape where basically there seems to be substantial vertical shear to the tidal flow in both directions, up canyon and down canyon. So if there is any slope in the isopycnals along the canyon, what this will do is it will tend to tilt that slope onto the vertical to the point where you get the cold water overlying the warm water and you convect and you mix. So we think this is what's happening in the canyon. It's not like there is shear-driven mixing linked to a small Richardson number or anything like that. It's simply convection induced by this vertical shear in the tidal flow.
So the overturn exists because of the shear. So I think it's a matter of terminology. If you didn't have that shear, you wouldn't have this process, would you?
Yes, the question is whether the shear, whether the mixing would happen if isopycnals were flat. So this is something that we need. We're currently doing some particle tracking with this velocity just to show that if isopycnals were flat, then you would need the shear to do the shear-driven mixing. But if isopycnals are like this to start with, which they are, then the shear has the potential to overturn the water parcels. So you need the shear. But if I'm turn out to be right, you need the shear not to mix directly, but simply to create the right conditions for convection.
I'm not disagreeing. There are two things. One is where the primary overturn gets its energy from. And shear has something to do with that. And the second is how it breaks, and that can be more convective or shear driven.
Okay, fair enough. Maybe it's a matter of semantics, but I think it's an important distinction, conceptually, because this is not the process that we normally think of when we think about mixing in the deep ocean. Okay, and just to illustrate that, I haven't cherry-picked one location where this kind of thing happens. These are the same sort of surveys as before in different parts of the canyon, and you can see those big tidal oscillations. The quantity shown is again the rate at which temperature is mixing, and the strong mixing doesn't happen always at the same phase of the tide, but it happens in association with this regions of very weak vertical stratification. So the way in which we've started to look at this is like a giant beach hidden in the canyon. So if you have that experience of going on holidays and to the beach and entering the sea, you know that there is on the offshore part of the shore, there is a region where waves are approaching the shore and they don't break, and then as you go farther onshore, there's a region where the waves start breaking, and at the very end of the beach there's a region where the bubbles fizzle out. So if you squint at that sort of pattern, that seems to be the kind of thing that you see here. But this is more a metaphor at this point than anything else. Okay, so just to try and wrap up quickly, the other thing that we did, as I mentioned earlier, was to deploy these specialized moorings that can measure directly the turbulent buoyancy flux. So this is something that hasn't been done before in the deep ocean because it's really hard. So normally we measure the rate of turbulent kinetic energy dissipation, or we measure chi, the thermal variance dissipation rate. It's very hard to measure the turbulent buoyancy flux directly. So this is the product of velocity fluctuations and buoyancy fluctuations. So in this case, buoyancy is kind of like temperature. So we're measuring the turbulent temperature flux. And the way in which we're doing that is by deploying lots of these instruments. These are called MAVs, modular acoustic velocity sensors. They sample at about 5 Hertz over about 3 months. They measure the 3 dimensions of velocity, and embedded within the volume that those parameters are measuring acoustically is a very fast temperature sensor, which is measuring temperature fluctuations. So basically you're measuring W prime or U prime, V prime, and also T prime. And you can, by multiplying all those things, you can get turbulent temperature fluxes. And just to give you an impression of the kind of information that we get, this is negative of the vertical temperature gradient from a number of these sensors deployed in the vertical, and you can see that beautiful structure with that tidal fluctuation. And you might recognize some of the patterns that we saw before. So those are the regions of very intense mixing and weak stratification or actually unstable stratification that we saw before happening here. You can see them in the moorings too. And from this kind of information, we can estimate the rate of upwelling, again, independently from the dye. So recall that the rate of upwelling was equal to minus the divergence of the turbulent buoyancy flux divided by the buoyancy gradient. And since we measure this guy, which is W prime T prime, and if we differentiate that vertically and divide by the temperature gradient, we can get an estimate of upwelling. So when we do that, we can get this derivative from, so the various dots here, each dot represents one of those instruments that I showed you earlier. So we can get this derivative from the differences between these values. And we can get the temperature gradient also from the temperature measurements of those values. So when we do that, we get that over this region, there is an upwelling of about a millimeter per second, which was roughly what we got from the dye. We're not quite sure what's happening here. So ignore that for now. Hopefully it will be resolved at some point. But hopefully this will give you an impression that of how the observations happen. You do a lot of the stuff, it's often not exactly what you planned. Then you do calculations, you can try and squeeze as much use of what you have, and you start bringing all the elements together gradually. So what we'll do next is do these calculations again and again and again, with increasing degrees of complexity and increasing degrees of thoroughness, until we are convinced that yes, these signals are really in the data and we're not making them up. But first indications are that there's a coherent picture coming out of this, where there is rapid upwelling along the boundary. It seems to be linked to this convective mixing happening with a tidal frequency, and but there are many different many gaps still in our knowledge of what's going on. Okay, so this is the sort of scenario that the pictures that I've shown you suggest so far. So on one face of the tide, we have this vertical shear in the up canyon flow, which is leading to tilting of isopycnals and convective mixing. And then on the opposite face of the tide, you restratify the boundary by bringing light waters from the top of the canyon down here. And so if you imagine the ocean flapping across its edges, up and down the slopes, we think this kind of thing might be happening with the regularity of following the tidal pacing, and that might be helping to mix and upwell waters at the very boundary of the ocean. So the next challenge we're going to face once we understand what's in the data is we're going to be asked, okay, you measure this tiny canyon that is 5 kilometers across or whatever. So what? It's so. It's the first thing that I would say is that these canyons, so a canyon is over here somewhere, these canyons are frequent in the boundaries of ocean. But the next question that one might ask is, does this happen also on planar slopes when you don't have canyons? And from what I've seen so far, there's nothing that seems to be, that would make me think that this is specific to canyons, but that's something that we need to think about and use models to help us in terms of understanding, how widely extrapolable this might be. And if ultimately we find that this kind of thing is reasonably generic, I think we may be facing a scenario where the deep ocean might be leakier than we thought, because it might upwell really easily along boundaries and then with some return flow away from the boundaries. But that remains to be seen. So I'll leave it there. Thank you.
Thank you. That was fascinating.
That's one polite way of describing it.
Yeah, thanks for a really interesting talk. So really cool experiment. Yeah, I guess my question was kind of follow on from what Ali was asking about earlier to do with this kind of, this tilting of isopycnals versus the kind of possible generation of shear instability. So maybe I missed it, but what was the angle of the slope that you added?
It's 6 degrees, I think, 6 degrees roughly.
So pretty, seems quite small.
It's small until you try and walk up it. It's several kilometers long, and yeah, I mean it's small, but it's not that small.
Have you sort of tried? Did you have lots of sort of local
we can, so we have those kind of preliminary versions of those kind of plots. One issue with making those calculations is that you can almost get any answer you want in terms of, depending on the vertical resolution of your data and so on. So you can get patterns, and the patterns will highlight where there is shear, which you can already see there. So it's going to be a little tough to disentangle these two things. I think what I'm really hoping is that, so one of the things that we're doing is we know what the mean distribution of temperature in the canyon is quite well from the moorings. So if you advect particles with the measured velocities at each depth, you can in principle determine whether the particles tracking the colder water will be able to overtake the particles tracking the warmer water. And if we find that that's not the case, then I would say that maybe this interpretation is wrong. If we find that that is the case, then I think maybe we're on the right track. But there's still a lot to disentangle.
There's maybe some competition between those two generations. Like Ali said, I suppose you could get overturned, quite significant overturn, just from shear instability itself.
Yeah. I mean, probably what's happening is that there's some degree of shear instability. I mean, yeah, the ocean has this habit of doing lots of things at once. And I suspect, so here we're just trying to determine what is the main thing happening. We're not saying that the other thing is not happening. Yeah. Yeah.
That's what Sam is looking at.
Yeah, sorry.
Okay. Excellent. Yeah, I'm sorry I have to run off now, but it'll be good to talk at some point.
Can I ask a very technical question? So you put some fluorescent dye, right? So the color doesn't matter. You show it's green. But...
Yeah, it doesn't really matter. It just needs to, you just need to be able to measure it with a fluorometer.
Yeah. So here's one question. What people thought about putting 2 or 3 dyes different from each other in terms of fluorescent properties? Then you can measure all of them. It's the same cost, right?
Yeah.
To deploy. But then you can measure all of them and see the observational scatter.
Yes, I think no, it's a good idea. It's a good idea. No, for a previous experiment, we think about that. So it is definitely possible. What I don't know is whether you need, whether with one single fluorometer, I can't remember whether you can configure one fluorometer to. I think you might need two different fluorometers flashing light at different wavelengths or something like that. But that's not a big deal. I mean, you can mount two instruments on the same fish, and so yeah. I guess at some point for a different experiment we thought about it, and we just thought we don't really have a good reason to do this other than it'd be fun. So we started. We ended up dropping it from the proposal.
Well, one reason is just to see statistical scattering, because if you have different measurements from the same deployment of the same concentration, just different, as you say, different chemical properties.
Yeah.
Statistical scattering.
Maybe that's the next level. Yeah.
This tilting isopycnol that's being rolled over, that sounds like a very low Richardson number scenario, right? Because it's energetically super costly to bring this whole to kill this whole isopycnol. So do you suspect that you have very low Richardson numbers, and in a higher Richardson number case, you will have a shear stability or something else?
I don't think there will be low Richardson numbers because it's a very turbulent environment. I guess, I don't really understand. I think it's a question of how the topographic drag gets transmitted vertically. There seems to be a preferential scale of something like 150 meters over which that drag is felt. And we're having arguments at the moment about what the dominant process is. So my thinking is not going in that direction. I don't think it's a low risk number environment. But having said that, I can't really give you a satisfying answer for how this happens. I think we need to look into it more, and we're actually going there this summer, and we hope to measure this in greater detail and in a way that allows us to understand what's happening. So one of the things that we're going to do is mount cameras on various instruments to actually look at the topography on the scale of boulders or whatever. We want to understand how this drag happens, how the kind of resolution that you get from ship-based acoustic measurements is very high. It's tens of meters. But I think for what we're trying to do, when you're trying to learn about the roughness of the bottom and so on, it might not be enough. So I think that's going to be our starting point, trying to understand the fine scale properties of the bottom even more and see if we can figure out why there's this vertical scale of the drag that seems to be linked to the vertical scale of the mixing. So I don't have an answer really, but watch this space.
Why do you choose to do these experiments in summer?
You've never been on a boat, have you? Well, we hope that there is no seasonality to this phenomenon. Okay, good.
Okay, so I just want to push back. I think, I mean, there's a bunch of us putting shear instabilities there. So I think when you say static shear instability, you're going to get a pushback.
Yeah.
But I think, I mean, this is obviously very cool. I think you might be overcomplicating the interpretation because, of course, the Richardson number criteria is from an analysis of parallel shear flow in an idealized setup, and we can make that more complicated with a boundary and slope isopycnol. But at the core of it, the question is if you're getting a change in some definition of vorticity, right? So and most of these instabilities, if you even think about baryclinic instability, so these are vorticity-based instabilities. And so you have a slope, and the flow gets imagine you have a no-slip boundary condition. But you can go into a reference frame in the middle of that it seems like the slope is going that way and the upper bound is going that way. So it's not that different from a shear that's generating an overlap. But you could interpret it that way. So if you look at the long slope vorticity of the mean flow before it rolls up, and you see a changing sign of that before it rolls up, then it means that it is a sort of Rayleigh-like instability. And then you can worry about defining a corresponding Richardson number or not. But if the question is if it is a vorticity-based like
Yeah.
stability or not.
Yeah, good point. Yeah,
If
that,
it is, then it becomes a matter of semantics whether we call it shear instability or not,
yeah.
and how it breaks. But
Yeah.
if it's not, then it's fundamentally different.
Yeah, no, good point. Yeah, I wonder about whether the geometry of the canyon, which gets narrower with depth, makes it somehow easier for those roles to develop. But yeah, that's a good angle, I think. Need to think about that. Okay. Thank you.
So much, Alberto. Right now, and I think we have some refreshments outside. And so we start again at 25 to 4. Okay.
No,
Hi, Wei, are you there?
Yes, hi, Ollie.
Great. Okay, hello everyone. So we're going to kick off the second half of the meeting now. And our first speaker of the second half is Wei Pan, who's a postdoctoral researcher here at Imperial in the project for stochastic transport of upper ocean dynamics. Unfortunately, Wei has COVID at the moment, so can't be here with us in person, but we have Wei with us through the magic of the internet. Spooky stuff, yeah. So if we could, if anyone has questions, if we could sort of hold them at the end and then we can bring the microphone around because the room isn't mic'd up itself. That would be great. Okay, Wei, take it away.
Okay, thank you, Ollie, for the introduction, and thank the organizers for the invitation. Yeah, I apologize for not being there in person today because of COVID. So if I have to cough, I apologize in advance. Okay, so the title of my talk is Numerical Data Simulation for Stochastic Vection by Lie Transport Models. So I thought I would take this opportunity to give you an overview of the baseline of techniques that we employ as part of the STEWARD project. Within STEWARD, there is basically several branches of investigation. And in particular, I work on sort of the numerical data simulation aspects. So most of these techniques were originally developed in a series of papers with Colin Cotter, Daryl, Dan Krisan, and Igor Shevchenko. So then that's listed here. We did for the 2D Euler system as well as the 2D quasi-geostrophic system. And then currently within STEWARD, we'd like to sort of take these techniques further and extend them and try to apply them to more complex, complicated models, as well as more complicated data. So if you're interested, so here are the list of references. So basically what we're doing is this realization of what's called a multi-scale salt algorithm. So the idea here, I know some of you are already familiar with this, but for those of you that are not, so basically this the idea here is we don't want to solve a deterministic PDE system using a very high resolution grid. So it'd be better in some sense to try to solve the same thing in quotation marks using sort of like a reduced model, but have more scenarios, more possible realizations. So that's the first step. So how do we sort of go from a deterministic PDE to some kind of a stochastic reduced model. And then we want to use data simulation to sort of keep the stochastic system on track with sort of the solution from a deterministic system. So in particular for us, data simulation means particle filtering. As I will explain, the vanilla particle filter will not work in this setting because of this high dimensionality issue. And so we need these additional techniques. So here I will discuss tempering and jittering. There's also nudging. So all these are sort of extensions to the basic particle filter that will enable the particle filter to work with these high dimensional data. So in this talk, I will just briefly review each of these ingredients. So here is the overview of the talk. I'll start with model reduction, and then we go into nonlinear filtering. Then I'll show some numerical results before I conclude. So, okay, so for those of you who are not familiar with the SALT framework, so basically the idea is, so Darryl, okay, so first of all, stochastic parametrization is not new, but as far as I'm aware, prior to this, most of the work has been concentrated on parametrizing the forcing term in the Newton's second law. But for us, so we're interested in parametrizing the transport operator. So via a stochastic variational framework, so Darryl derived this stochastic Euler-Poincare equation. So this is very, very general. So basically you have for different Lagrangians, you end up with a different model. But basically here, this additional term sort of models the error in the advection due to this reduction of scale. So the stochastic model is sort of will try to capture the large scale behavior of the flow on the coarser scale. And then we have a very similar approach called the location uncertainty. So that's sort of similar to SALT, but the difference is that SALT equations were derived in a specific way that preserves the Kelvin circulation theorem, whereas the LU, or location uncertainty, that sort of first introduced in 2014, was designed to preserve energy. And then currently within STRUD, sort of these two approaches have come together, and so we're all part of the STRUD project. So okay, so the two example models I will show today. So one is the work that we did previously with Colin, Darryl, and Dan and Igor. Is this two-dimensional Euler, and then I'll also show you on the next slide this thermal quasi-geostrophic equation. So here, as I've mentioned, basically you have this PDE system that you would need to solve. You need to solve using a very, very fine grid in order to have an accurate representation of the solution. But we can sort of, via this model reduction, we end up with this additional stochastic term. So we end up with this stochastic PDE system. And then this term sort of models this the error due to this scale reduction. So the added complication here is that you have this vector field, which we call Xi or Xi, that is sort of unknown a priori. So in order to sort of accurately do this model reduction, we have to calibrate and get this Xi vector field correct, so that in a distributional sense, the SPD system will is able to capture this PDE system. So here, this U bar is sort of, you can think of sort of the mean, the averaged velocity field U, and then this Xi Brownian motion term captures sort of the fast fluctuations. So the Okay, so the 2D Euler is something we worked on previously. Currently within Stewart, one of the systems we're looking at is this what's called the thermal quasi-geostrophic system. So this basically has a Hamiltonian formulation, and it was sort of developed using a nested asymptotic expansion of a thermal rotating shallow water model. And so if you throw out all the higher order terms and you keep basically the first order terms, and then you end up with this equation here. So it has two dynamical equations. One is the potential vorticity, which I've denoted using omega. And then you have B, which is buoyancy. And then the interesting thing is this particular term here, which is the, you have UH, which basically is the grad perp of the bottom topography or bathymetry. And then this sort of dotted with the gradient of buoyancy, it acts as a forcing term in the PV equation. And then, yeah, this is sort of like the interesting interactive coupling term that sort of generates many of the sources of instability that makes the numerics very challenging and also makes the analysis quite challenging. So far for this system, we don't have global well-posedness, but there is a local well-posedness, meaning solution only exists up to some given some stopping time. So okay, I won't go into that. If you're interested in looking at the analysis and the derivation of this equation, then these are the two papers to look at. So all right, and then just to I'll sort of give like an idea of sort of the computational reduction. So these were the numerical parameters that we used for the Euler system. So basically, we used a 512 by 512 grid, and then with this type of time stepping size. And then for the SPD, we were able to achieve quite a large reduction. And then you can have a sort of a larger time step with so it's much cheaper. And then basically we sort of use the same ballpark figures for the TQG system. However, due to that problematic or interesting term, actually for the TQG you have to go even smaller than this. So either that, or we have to artificially introduce a dissipation term, or something else we looked at was using alpha regularization to sort of to control the development of these instabilities, so that we can take a larger step. But I won't go into the details on that. And the way we measure timescale for the Euler system was using these eddy turnover time idea. So basically, it's basically sort of the time scale that corresponds to the largest eddy, and then one sort of intuitive sort of interpretation of one eddy turnover time is like a 1 month. So okay, then so I want to put this up front. So we're doing the parameters we're choosing are sort of we're pushing. We're at the limit of our computational limits. So we don't have like the supercomputers that the Met Office has. We just have these two workstations. And so I'm showing a photo. So this is in my office. This is Beast 1. We call Beast 1 because it's quite a big machine and it's quite heavy. And it's got 32 cores, 64 gigabytes of memory. And then we have also now a second machine, so Beast 2, that runs the TQG model. So it's newer than this one, so it's got a bit more cores and a bit more memory. But still, yeah. So we can't sort of go more than the numerical parameters I showed on the previous slides. So okay, so now I sort of give an overview of the calibration approach. So the first one I want to show is this physical approach. So for transport noise, most, not all, most of the calibration techniques that's been employed in the literature are based on the physical interpretation of the model derivation. So meaning that if we go back, so the assumption here is that basically we can, the fluid trajectory, you can sort of, we assume it moves like in this stochastic way. So we have this scale decomposition into like a mean part and the fast fluctuating part. So this is, and then so in our calibration, this is what we try to do. We basically do some kind of a smoothing on the PDE solution, the fine resolution solution, to get the mean part. So that's this U bar. And then we look at the difference in the Lagrangian traces to give us some kind of like an error. And from that, we know this is a Gaussian process. So then really what this thing, the vector field here should be is the eigen function of the covariance tensor. And then, by the way, this is a very famous picture, originally by Colin. So I've kind of replicated here. And so that's exactly sort of illustrating what this equation is representing. So you have this fine resolution trajectory doing all sorts of wiggly things. And then we compare it over a short time interval. So to the difference, if you sort of do the same, if you start from the same position, then what would the mean flow would take you? And then that will give us some kind of error at the end point. And then these will sort of be the data that we use to try to estimate the covariance structure of our model for this error. So that's what this physical interpretation is about. And then basically once you have this data, you just follow like this EOF, the empirical orthogonal functions procedure to get the C's. And then we don't have to use all of them. Well, we can, what we've done is you can sort of use only a subset of the total number of C's. And then so here you're saying so to capture like 50% of these variations, you need 51 size. Here it's 107 to capture 70%, and you need 225 to capture 90% of the variability in these Lagrangian trajectory differences. So these were the numbers that we obtained for the example Euler system. So the coarse graining, so in order to extract this mean part, we use the Helmholtz operator. So here at the top you see the sample snapshot of the Euler PDE, the two-dimensional Euler PDE. So you have the vorticity field, you have the velocity field and the string function, and then we apply this Helmholtz operator to smooth out the string function to get this, and then use the PDE operators to then recover the vorticity and the velocity field. And then so basically our U bar is then of this picture here. So okay, and then for the TQG, we basically do sort of the same thing. The reference PDE solution, we used these set of parameters. So the PDE is solved again on 512 by 512 grid. We assume it's in a horizontal channel, so it's got a Dirichlet boundary condition in the X variable, but it's periodic in Y. And then, as you can see here, we use a one order of magnitude smaller delta t compared to the Euler system. And the interpretation of this size for this particular reference is that it's one time step is about 3.5 minutes. And we solve the time horizon is from 0 to 8.275. I don't know why, but just 8.275. And then the SPD we discretized using a grid of 128 by 128. So this is a reduction of 16 times. So, okay, and then a particular interesting thing to note here is this string function minus half of buoyancy in the TQG setup is interpreted as the sea surface height field. So, okay, so using those parameters, this is the snapshot of the fully spun up solution that we get. So we call this reference the angry dolphin for reasons that I will show you now. So this is a video we put on YouTube of the PDE reference solution, and then at some point the equation drew this bit here, which looked to me like a dolphin looking angrily at this red wall. So that's why we call this angry dolphin. So what this video is showing, so I'll just quickly play a little bit of this, is the creation of the buoyancy front from the initial state that I showed on the slide, and it's and the subsequent emergence of various instabilities. So yeah, so it generates basically like a cascade of smaller mushroom-like dipole circulation and also trains of Kelvin-Helmholtz roll-ups via the interaction between the buoyancy and bathymetry gradients. Okay, and then at the end, it reaches the fully spun up state, which is the snapshot. Yeah, here. So yeah, and then the interesting thing here, if we apply the calibration technique, what you notice is to sort of capture the same number of variabilities, so we can get away with a lot fewer EOFs. So you only need 4 to capture 50%, whereas for the Euler system, you need 51, as the numerical result shows. So the reason for that here is that if you sort of look at the video again, this flow, basically you end up with these very persistent large coherent structures, whereas for the Euler system, that the domain there was a square with fixed walls everywhere. So it's sort of just mixing within this fixed region, whereas here you have like this flow just continuing, and then yeah, and then so here's a picture of one of the first EOF. So the eigenfunction with the largest eigenvalue. We call this the elephant function because this captures a lot of the variability. So yeah, so it's like the elephant in the room. And then if we go down the list, then here you have the snakeskin function. So this is EOF 35. So showing really sort of for that flow, these small scale patterns have much less contribution to the variability. So okay, so here is another approach we recently developed. So this is a pathwise approach rather than the physical approach. So the paper here is currently on arXiv. It's been submitted to the Stewart Proceedings journal. So the idea is to use since we have sort of a kind of like since we have like a semi-martingale system, so we can try to if you just choose some orthonormal basis for the psi or for the string function of psi, then if you do the calculation for any sort of observation function applied to the vorticity. So here below is just this is for the Euler system. Then the quadratic variation of this is given by this formula here. And then what you end up with is basically a quadratic form, which is positive definite. So it can be diagonalized by a unitary linear map to then sort of reduce this to a simpler looking system, where the lambda are the eigenvalues of the associated linear map, and these alpha tildes are the rescaled alpha. So the alpha corresponds to the coefficient that's in front of basis element j. And so we wanted to test this. So here you have the formula for for the quadratic variation. So it's just the sum of square differences at different times, and then it should give us this. And also this methodology is backed up by a robustness result, which basically saying if we sort of don't quite exactly recover the same psi, then what does this mean for the solution? So this theorem is proved by Wana Lan, who's in the audience, and then basically it's kind of like a Lipschitz result. So the L2 norm of the solution at any time is sort of bounded by the difference in the initial data as well as the difference in index size. So this sort of supports why this methodology would work, even if we sort of don't quite get the size correct. And then here is the numerical example that we did. So this is a sanity check. So we assume basically one psi with one coefficient, and then on the left here you see the estimate. So this is using the sum of square differences. So that's this formula here that we implemented. So you get this image here, and on the right here we assume we know exactly what the basis is. So here is an exact sort of implementation of the formula for the basis. So you can see already that given sort of these many data samples, which seems quite a lot, but I'll show on the next slide that you can get away with much less. You basically have sort of this very, very accurate recovery of what this basis should look like. And then to get back the alpha, you just divide one from the other. And how accurate is that? So using the full set of using the full set of high frequency snapshots of the solution, we were able to get very, very accurate approximation of the true alpha value. This plot is in log scale. You may sort of try to think of the sum of square differences as some sort of like Euler discretization, in which sort of in a strong pathwise sense should have perhaps would have an order of a half, but that's not the case here. The convergence rate for that sum is something we're trying to understand. But already, so if you use sort of only 2,500, you still sort of don't get that much different estimate of alpha. So it shows that at least in this very idealized setting, it shows that the methodology works. And then we're working on ways to extend. So this is like a pathwise calibration approach. So all right, so I'll now give a brief overview of the filtering problem. So if you're not familiar, this is the data assimilation part. Basically, we want to, so you have X here, which is the SPDE, and then we want to basically compute or estimate the distribution of the SPDE given what we observe about the PDE system. So this data-driven, so this is sort of the data-corrected distribution of the SPDE. So this is the main, I guess, the second main part of the Steward algorithm. Really, to do this, you follow the Bayes recurrence relation, which is you can do like a forecast prediction step and the correction step. So the prediction step means you take your current ensemble, you just run your ensemble forward until the next observation point, and then you get your data, and then you update the likelihood of each of your particles by comparing them with what's being observed. So that's this update step, and then so if you sort of do this recursively, you end up with like a numerical algorithm that sort of tracks tracks what the posterior distribution, what the filtering distribution is. And then the particle filter is like a Monte Carlo approximation of this procedure. So instead of so before is everything is in continuous time. So here we use like an ensemble to approximate the filtering distribution. So this is exactly sort of doing the Bayes recurrence relation. So we first start off with a bunch of particles in the current posterior. You sort of then evolve the each up and forward according to the equation, and then you update using the you update their likelihood using the likelihood function, which is G. And then you don't want to sort of track the probability of each particle. So we want to resample by killing off particles which are not likely and then keep the ones which are likely. However, now is the problem with particle filters in high dimensions, is this singular distribution problem. So given that you have this high dimensional observation, really what you if you look at the likelihood, what you really you just have the concentration that you basically have all of your particles killed, and you will only end up with one particle that survives when you do this resampling procedure, which is why you would need tempering and these tempering and jittering steps in order to sort of smooth out this transition, to always keep your population, your ensemble within the concentration of the probability measure. So that's this tempering step, and then and this needs to be coupled by jittering. I don't have time to go into the details, so if you're interested, I'm happy to have a chat offline, or you can look at our papers. So just lastly, so our data for the Euler system, we considered fixed weather stations. So i.e. the positions, we only took data at these fixed locations. I hope you can see the yellow dots. And then that doesn't change with time. Currently, I will skip this. And for the TQG system, we want to go a step further. So we've simulated. So we're considering simulated satellite track observations. So here is so here we have two satellites, satellite 1 and satellite 2. So basically these equations are just the projection of some helix onto this torus flat torus domain. And then you have these K1 and K2 parameters giving you like how many loops it goes around this donut. And then each of these satellites has this parameter phi, which controls the phase transition periodicity. So we're trying to do this as realistic as possible. So we know from our colleague that real satellite tracks for observing like the sea usually have a periodicity of about 10 days, meaning that the satellite would return to the same position, exactly the same position above Earth once every 10 days. So here is...
I wait, just to let you know you have 5 minutes.
Okay, thank you, Oli. So here is a pictorial representation of the simulated satellite observations of the TQG sea surface height. So yeah, so we are choosing to observe the sea surface height field, just like what the real satellite would give us. So on the left here, you see a fine resolution snapshot. So this is the PDE, fine resolution snapshot of the sea surface height. And then we basically, I've overlaid the satellite tracks on top of the coarse grained sea surface height here on the right. So you have, I hope you can see this. So there's this pink line that's satellite 2. And then you have this this bright green line that's satellite 1. And then I'll just very quickly show you the video of this. If I speed this up, so you can see the satellites moving. And then we, at any one time, we just basically evaluate evaluate the whole coarse grain sea surface height along these lines. And then that's our observation data. So, okay. And then to show you why we're doing this, so this is a screenshot of glob current, which is this, I guess it's in partnership with the European Space Agency. So these are real satellite tracks observing sea surface height. And then, yeah, so we're trying to do things as realistic as possible given our computational limitations. And then you can see sort of the satellite is stopped here. Well, I mean, it's still sort of going around the Earth. So when this snapshot is taken, it's that's the position of the satellite. If you're interested in playing with this, and just go on Google and then search for glob current, and then yeah. So all right. So I probably don't have time to go into here, but I guess what I'm trying to say in this part is that yeah, we have a lot more data, and then something we didn't consider for the Euler example data simulation was that these spatial observations have some kind of correlation. So we can do some kind of reduction to sort of do a reduction on the observation space to make the simulation easier. And then there are various techniques of achieving that. And then finally, just to show you how particle filters work. So this is some results we got for the Euler system. So these are Eulerian. So each picture here is an Eulerian trajectory comparing the truth, which is in this solid red line. And I hope you can see this. There are some like sort of pink-ish spikes around the red line. So the pink spikes represent the size of the actual realized observation noise at that particular point. And then the blue line is the posterior ensemble mean. So that's the pi t, the filtering distribution, the mean of the filtering distribution. And then you can see that given only 1,089 observations, the SPD ensemble is sort of tracking the true PDE solution. And then compared to the yellow, so without data simulation, so this is just running the SPD forward without any data simulation. You can see it's much farther from where the truth should be. And then just finally, here is rather than the ensemble mean, I've plotted, I've put in the actual SPD trajectories. So you can see that the spread is a lot more than if you sort of have a data corrected ensemble. So right, and then I'll wrap up. So we applied particle filter with 3 necessary additional procedures to the Euler system. So these then serve as the baseline algorithms that we're currently employing for the Steward project. And then we're trying to make everything work for this more complicated TQG system, as well as this more complicated simulated satellite data. So there are still some challenges, and we hope to overcome them as soon as we can. So if you have any, so thank you for your thank you for listening, and then if you have any questions, I'm very happy to answer. And here are some references.
Thank you, Wei. We have time for one quick question, if anyone has a question. Okay, Daryl.
Wei, when we look at the last set of figures you showed right there,
yeah,
maybe you could just go through again. Does the last step actually crush the accuracy right down to the truth? Is that what's happening?
That's right. Yeah. So okay. So here I'm showing the actual ensemble, whereas the previous image I'm showing that the ensemble mean. So here the solid red line, I hope you can see this, is the actual Eulerian trajectory of the truth from before, and then sort of the ensemble of posterior particles. So those are the data corrected SPD trajectories. You can see sort of stays very narrow and very close to the truth. But these sort of orange and yellow trajectories, they are the SPDE trajectories starting from the same initial condition without any sort of data correction. So if you just run the SPDE forward, they don't track the truth. They just sort of spread out and then do go in their own ways. So I'm just want to highlight that the data correction really is doing something to the ensemble.
So thank you, Wei. I expect that this means that ordinarily when people talk about turbulence and as some kind of diffusion, obviously nothing is diffusing here. So what we're dealing with here is actually transport, always transport.
Yes, that's right. We don't have any dissipation in our model. So it's purely transport, folding, stretching, these kind of things. So it's not quite turbulence.
Okay, thank you, Wei.
Thank you.
If we could thank our speaker again. Let's go back into the in-room mode. Yeah, if you just like to Okay, so our next speaker is Matthew Crowe, who joins us from across town. He's a postdoctoral fellow at University College London and did his PhD in Cambridge, and is going to talk to us about ocean fronts today.
Technical problems. Oh well. Okay, thank you. So today I'm going to talk a bit about some work I've been doing over the last 6-7 years on modeling ocean fronts. So this initially started with my PhD with John Taylor in Cambridge, and is something I've been continuing on and off alongside my postdoc work in UCL. So I'm probably going to end up asking more questions than I answer by the end. I'm going to try and give a sort of overview of modeling philosophy type thing. So just as an overview, I'll start with some background and motivation, then talk about mathematical modeling of ocean fronts in a simple 2D setup, before moving on to the 3D case where things can become unstable, and then summarize things at the end. So the main motivation for a lot of this work is the ocean energy balance. So I'm going to end up repeating actually some of the content from our first talk this morning, which is very helpful. So the basic idea is that energy enters the ocean at very large scales. This is through winds forcing basins, as well as other effects, including, say, solar heating, tides, and then there's some other things that are sort of less relevant overall, such as ice melting and freezing. So all that energy goes in, then loads of stuff happens, and eventually a lot of that energy comes out. It's dissipated as heat at small scales by molecular processes. However, there's a bit of a problem in getting from here to here. So part of the problem is that energy enters the ocean at these very large scales. These very large scales are controlled by 2D geostrophic turbulence, and the cascade there wants to send energy up to large scales. So that's not going to help with dissipating things at small scales. The other problem is, well, our ocean simulations, which we use to look at a lot of this stuff, they can't resolve small scale motion. Even the best simulations we have, if you were to run on a global scale, you can maybe get 10-kilometer resolution. These small scale things need 1 kilometer, 100 meters, maybe smaller. So we're not anywhere close to actually resolving these things. A lot of the theory we have on the large scale isn't going to give us the answer. So we're going to have to kind of understand these small scale processes in order to work out what they do, with the eventual goal of being able to parameterize them in some way in our large scale models. So a bit of background before getting to ocean fronts, the surface mix layer. So this is the top region of the ocean. It's anywhere between 10 and 500 meters, depending on location and season. So these pictures here, probably quite small, but these are mixed layer depth estimates based on vertical profiles. And important feature of the surface mix layer is the middle word. It is well mixed, and that mixing is due to elevated turbulence. And this turbulence comes from a whole load of processes, things such as heat flux, wind, evaporation, wave breaking, ice, and so on. Because of that, this upper region is very, very active, and you get a lot of small scale things going on. One of the things that happens in the surface mix layer is ocean fronts. So these are important sub-mesoscale features, and they occur typically on scales of 100 meters to 10 kilometers. So an ocean front, that is a region of strong horizontal density gradient. So this picture here shows the Gulf Stream coming off the coast of the US, and we have some warmer water here coming up, meeting colder water above. Across here, there's a sharp transition region between the two. That is an example of an ocean front. And there's an example of a front in the Atlantic here, just off the coast of the UK. And there's a red dashed line you probably can't see just along here, and between water of different temperatures. So these fronts are long in horizontal direction, quite thin, say in the cross front, it's the direction across the front, and they're also quite shallow. So they exist just in this top mixed layer of the ocean. So they can generally be around 100 meters in depth. This is shows here a profile from a study. They took a boat and they measured density profiles across this front. So the region here shows the front, and this depth here is about 100 meters or so. And important feature of these fronts is they have very high vertical velocities for the ocean, that is. And this means you get a lot of exchange of gases between the ocean and the atmosphere above, and between the surface mix layer and the deep ocean below. These gases include things that are quite good for biology. So you get a lot of phytoplankton in these areas, which means you end up with a lot of marine life as well. So to model simple ocean front, you just consider a region of high buoyancy, which is light fluid, just here, next to a region of low buoyancy, which is dense fluid here on the left. So we've got two regions next to each other. Then we have a transition region in between. So that is the front. And we have a buoyancy gradient going from the low buoyancy to the high buoyancy side. And we're going to say the width of this front is L. Layer depth is H. And we're going to rotate this system with Coriolis parameter F. We're going to work in coordinates X, Y, Z. X will correspond to the direction across the front. Y will correspond to the direction along the front, then Z is vertical. So initially for our 2D model, there's going to be no variation in the Y direction. So to get some intuition about what's going boundary conditions. So that will get a bit more complicated later. So generally consider W equals 0 on the top and bottom. And then if you have some viscous boundary condition, which I will later, you'll need no stress and no flux on the top and bottom. Yes, it is, yeah. So the simple first approximation is a closed box. You can later have a deep ocean below that, which requires then just a boundary condition of matching to that. So force balance to start with, your acceleration is equal to the forces in your system, which are the Coriolis force and the pressure gradient. Typically, for these structures, the Rossby number is small, which means that your acceleration is small in some sense. So the dominant balance here is between Coriolis force and pressure gradient. And that gives your thermal wind balance, which says that to leading order, your velocity across the front is 0, and your velocity along the front is given by a vertical profile that increases upwards, because in this setup, dB by dx is negative, and dB by dx, that is your horizontal buoyancy gradient.
Hydrostatic conditions.
Yes. Yeah. So yes, it's assumed to be hydrostatics. Your pressure is just your height times your density. So you end up with a flow, your thermal wind directly along the front, and you have a thermal wind shear because your velocity increases as you go upwards. However, thermal wind balance can be disrupted by a variety of processes that generate other velocity components. And those velocity components can then knock the front away from thermal wind balance, at which point the advection that we have neglected up to now becomes important and can act to further push the front away from thermal wind balance and sharpen it. And this sharpening is quite a complicated nonlinear phenomenon. It's known as frontogenesis. The early inviscid theory on this problem suggests that your front will continue to sharpen indefinitely in some cases, and then can become infinitely thin. However, this seems to be unphysical, so we haven't observed any cases of infinitely sharp fronts in the ocean. There seems to be something setting a horizontal scale. The next thing to do is to take the simple thermal wind model and to add in some more things. So we'll start by adding in strong turbulence. So this, as I mentioned before, exists in the surface mixed layer. And a common representation for turbulence is an eddy viscosity or an eddy diffusivity. So here we just represent turbulent motion as a diffusion-like process. And we say there's a viscosity and diffusivity, and we can scale those based on some turbulent length scales and time scales. Naturally, coming up with a representation for this thing is a whole field of literature in itself. So once you've got some representation for your turbulence, you can include these new terms as viscosity or diffusion terms in your governing equations. So if you include the turbulent, diffusion, and viscosity terms at leading order in your force balance, you now have a three-way balance between the Coriolis force, pressure gradient, and these diffusion terms, which is given here. So you have your Coriolis force terms here, pressure gradients here. There's no change in the along front direction. And you have some diffusion terms, where here I've only kept the vertical diffusion terms because the vertical length scales are a lot smaller than the horizontal length scales. So these terms end up being bigger by a factor of the aspect ratio squared. That's true, they can. Well, when I do the full thing, I include both, and then you can modify them to whatever you want. But for this simplified case, I'm just going to stick to the vertical bit. And this system is known as turbulent thermal wind balance. So it's thermal wind balance with this extra turbulent term. And the solutions to this system depend on one parameter. That parameter is the Ekman number. This has been non-dimensionalized. So the Ekman number describes the strength of the turbulence relative to FH squared. And we can solve this system analytically. It's a fourth order ODE in Z. So that's quite straightforward. If you include the horizontal terms as well, you just have to solve it numerically. E is assumed to be order 1 here. So in reality, E can be around 10 to the minus 2 up to 1.
The terms that Pablo referred to, if you were to keep them, what would be the physical interpretation of the horizontal diffusion point for what you're trying to do? Dystrophic field.
Yep.
Then that would those would represent the dystrophic. Makes sense. Or
Yeah, they would represent horizontal transport by small scale ageostrophic mixing.
and do you have a sense of what that horizontal diffusion coefficient would be like in terms of order of magnitude?
Generally similar or not a huge amount bigger than the vertical one. So 10 to the minus 2, 10 to the minus 3 meters per second squared.
So in that case, this one dominates.
In that case, this one dominates, yeah.
So am I right that by diffusion here, you basically model some small scale instabilities?
Yes, exactly, yes. Yeah.
So if you know what the instabilities are, you can make some assumptions about.
Yeah, and I will get onto that later. Yeah. So this is what that solution looks like. Equations are a bit of a mess, but the pictures show this is your along front velocity. So this is very similar to what we had before. You have a vertically sheared jet running along the front. Here, everything's going to be assumed to be symmetric about the center. So you're going into the page at the top and out at the bottom. The effect of the vertical mixing terms is to couple the cross front and along front velocities. So now you end up with velocity flowing across the front here, back from the high buoyancy to the low buoyancy side, and symmetrically at the bottom. So what you have is a velocity that will act to slump your contours over such that the light stuff runs across the top and the heavy stuff goes across the bottom. And because of that, you can use mass conservation to calculate the vertical velocity, which says that there is a flow upwards along the light side and downwards along the heavy side. And then this cross-front velocity shear leads to a spreading of the front through shear dispersion. So what happens is you start off with your contours initially vertical. You have a stronger flow at the top than you do at the bottom, so that tilts your contours over. Then you have this strong vertical mixing, which mixes up and down, and the end result is that your frontal region is now wider because it now goes from that and the new top to that bottom there, giving that total region from there to there is wider than what we started with. And this shear dispersion can be thought of as the shear is projecting your vertical diffusion horizontally. And we can determine the rate of spreading by going back to the buoyancy equation, plugging in the form of velocity that we have, and that allows you to derive a diffusion type equation where instead of simply being dB by dx here on the right hand side, you've got a cubed up there. And we can solve this using a similarity solution. You have 1t over there, 4x's on the bottom over there. So you find that your front spreads with the width increasing with t to the power of a quarter. And this is slower than traditional diffusion, which is t to the power of a half. This picture here shows the center line buoyancy. So that is the buoyancy across the middle as a function of time and cross front direction. And as time goes on, this region slowly spreads out. And this spreading will act to oppose the sharpening caused by frontogenesis. And so if we run some fully nonlinear numerical simulations, we can stick the Rossby number to no longer be small, stick that as whatever we want. And we can find that there's a few different regimes here. We have this critical frontal width LC, which depends on our Ekman number. And for widths larger than that LC, then the mixing is strong enough to prevent the front from sharpening. And conversely, for lengths smaller than that LC, the mixing is not strong enough to prevent the front from sharpening, and it collapses down to what in the numerical simulations looks like grid scale. So the existence of these two regimes suggests somewhere in the middle, could be a case where if L is equal to or close to LC, you may get an equilibrium where the sharpening effects of frontogenesis are counteracted by the spreading effects of shear dispersion. So now, up to now, we've considered a 2D problem. However, if we allow variations in the y direction, the along front direction, the question becomes, is the system stable? And by which we mean, if we change it slightly, does it go back to where we started, or does it move towards a different state? And we can often get some idea of what might happen if we think about the energy of the system. Certainly.
The vertical mixing, what is the physical process that you have in mind?
I will answer that in about 10 minutes' time. So, as I said, fronts consist of a heavy region next to a light region. Okay? However, this isn't the most energy efficient state. That would be well, the lowest energy state. That would be light stuff on top of the heavy stuff. So that suggests there's a large amount of potential energy here that's available, and that potential energy can be accessed by converting it into kinetic energy through instabilities. And there's various other possible instabilities, including things powered by velocity shear through that kinetic energy. And these pictures here show a survey of what was initially a straight front that has over time rolled up into these vortices. And this is an example of baroclinic instability. So moving to a 3D stability problem, we have the same setup as before, but we allow variations in the y direction. And we take our 5 fields, 3 velocity components, buoyancy and pressure, and we write them as our turbulent thermal wind solution from before, plus small delta times a perturbation. We can then take this form and stick it into our full 3D equations, and we can ignore any terms of order delta squared and higher to linearize the system. And we can then solve for perturbation quantities.
So is your thermal wind background state with vertical viscosity?
It is, yes. Yeah.
With,
yeah. So the system for the perturbations is linear. So we can assume these perturbations take an exponential form, which is ikx plus ILY in space, and then sigma t in time. This is just equivalent to Fourier transforming your system in x and y. And these coefficients here with hats, they're just functions of z. So we can take this form, stick it into our eigenvalue equations, and we end up with 5 governing equations that can be turned into a single matrix equation, where here M is some big matrix that depends on K, L, and d by dz. It also depends on the Ekman number through the background state. And sigma here is our eigenvalue growth rate. So if sigma is positive, this exponential grows and your perturbation will grow with time, indicating it is unstable. So, yeah.
So you've introduced y once again a little bit to
Yes.
not introduce, so we sort of neglected the y dependence in order to form the equations that we're dealing with in the first place.
Yes, so at this point, what we have is the background state equations are just the 2D solution. So the background state is purely 2D and doesn't vary in y. The perturbations are included and are allowed to vary in y. So what we end up with is the bits in capital letters are functions only of x and z. And then this bit is allowed to vary in y.
How come your sigma is not obvious?
It can be real, complex, whatever. You can get traveling waves, which would be complex, or you can get growing or decaying solutions, which would be real.
But the last line is about real parts.
True, yes, that should say real part of sigma. So gonna think now about baroclinic instability. So in the non-turbulent case, with Ekman number equals 0, this has k equal to 0. So that is the cross-front wave number in the x direction is 0. And what happens is if you start off with a straight-ish front, as time goes on, you get wave-like perturbations appearing in the along front y direction, and then over long times, these become nonlinear and roll up into vortices. And the question now is what happens when the turbulent effects are included and the Ekman number is non-zero? Well, two important things are seen. So ignore for now the Prandtl number here. But what happens as we increase our Ekman number here, the modes become angled. So they're no longer directly aligned with the front. They take some angle to the cross-front direction, which I'll show in a bit. The other thing we observe is that the growth rate, sigma, or the real part of the growth rate, decreases with Ekman number. So instabilities will grow slower for stronger turbulent mixing. And this is verified with numerical simulations. So here I'm plotting B prime, so that is the buoyancy perturbation away from the background buoyancy gradient. And if E was 0 here, we would expect our waves to be directly in the y direction. However, we now see some angle, and this angle appears to match the dashed line, which is the theoretical prediction that I've not shown. So as this is B prime, I'm not showing the front, but the front would be in the x direction here. This is, again, it's the center line, so through z equals 0. These figures here show the evolution of this instability. So we start with some small random noise, enter a linear growth phase. The modes then roll up, and eventually you get a cascade towards larger scale motion. Okay. So we observe that these instabilities seem to be damped by strong turbulence. Is this at all relevant to real life? Well, the Ekman number is smaller in the winter generally because the mixed layer depth is smaller. Therefore, our instabilities are going to be damped more in the summer. And something we do observe is that there is reduced submesoscale activity in the summer. So that would appear to agree, though I'm not going to go and say it's the cause.
Actually, the Ekman number has the denominator, right?
Yes.
So if the depth is smaller, then the Ekman number is larger.
The mixed layer depth is also bigger in the winter. I've written the wrong word. You are correct, yes. And that should say mixed layer depth is larger. So last bit on mixing. So we've assumed throughout that the Ekman number E is fixed and represents some mixing process in some way. However, the instabilities we've seen, they're going to be susceptible to secondary shear instabilities, which will in turn be susceptible to shear instabilities, and so on. And you'll generate smaller scale eddies, and then eventually you'll have a 3D turbulent cascade. Yeah. Yes, or vertical, any really. If it's a fully 3D problem, you're going to get mixed mode shear instabilities with horizontal and vertical bits. So your instability will generate more small-scale turbulence through this 3D cascade, which will be increased through the initial instability. So we end up with a complicated feedback mechanism where the structure of the front is affected by the Ekman number, as is instability formation. They both modify the turbulence through the generation of instabilities, and the turbulence can feed back and modify the mixing, and hence the Ekman number. Returning to what I said at the beginning, small-scale turbulence is expected to be responsible for dissipating ocean energy. So 2 questions we could ask are, can we use our understanding of ocean fronts to estimate how much energy they dissipate through the generation of instabilities? And the next question is, as these fronts are too small for global ocean models to resolve, how can we, if we've answered question 1, how could we take the answer from question 1 and build that into a parameterization? And to conclude, turbulent thermal wind balance allows for turbulent effects to be considered when studying ocean fronts. And the effects of turbulence seems to be to drive across front velocity and spread the front. The spreading can oppose frontogenesis and may lead to an equilibrium. The keyboard seems to have stopped working. Oh well, you're going to have to miss the last slide. Oh well. Thank you. Any questions? Yeah.
In the envisioned theory, which is all I know, the frontogenesis starts as a baroclinic instability in 2D X and Z, and so you've got a sort of large scale wave that gets turned over until it becomes a small scale feature.
Yeah.
So you said that if the front is kind of larger than a certain width, then it never forms in the first place, which seems to contradict the way we get down to a small scale front is from a large scale pattern. The map is sort of if the pattern is smooth enough, then the front never forms.
So I haven't thought of it in that way, but from what I'm seeing from the simulations is, if you make the Ekman number small or 0, you have to start out of balance, otherwise it doesn't sharpen. But what happens is you get an advective tendency in the top and bottom regions, which drives a convergence up the top that then pinches the contours together. And if you have strong vertical mixing in that region, you have as your contours are pinched together, things get mixed away vertically. So it never quite sharpens to the same.
So you're assuming it's always in fact exact balance?
Not necessarily. So similar things happen. If you start too far out of balance, no amount of mixing is going to help. It will just collapse down. But if you start either in balance or not too far out, you end up in the same kind of equilibrium case where it moves towards it, never quite gets there, then gives up and spreads.
In the semi-geostrophic theory, it's the ageostrophic wind that drives the frontogenesis.
Yeah.
Okay, great. We could thank our speaker again. Okay, we're running a bit behind, so we'll move straight on to the next bit. Several minutes. No. minutes.
Huh?
Do you want me to give you 5 minutes? Okay, we're having a slight technical problem, so there might be a sort of a 5-minute delay. We have the wrong slides on the computer.
Oh, right.
still works.
But can I use that?
Yeah, you can use one of these.
No, I just need the one app. Yes, I see it in 3 different.
Yeah, yeah, it's Velcro.
Sounds. Oh, because it's still on the Zoom.
Yeah.
This hurts my brain.
I know it.
So is this still working?
Thank you for the break.
Yeah.
That was really useful. I'll tell you why.
Is this working? Yeah.
Yeah.
Okay.
It was louder in the Zoom, but it wasn't.
So that's okay. Yeah, I can.
Yeah, if you could.
Oh yeah, thank you for Sorry about that.
Okay, guys, we're gonna restart. So I'd like to introduce our final speaker of the day, which is Laura Cimoli, who is joined us today from Scripps over in San Diego. So yeah, we're very happy to have her here. Yeah, take it away.
Thank you. I'm sorry for the technical difficulties. On the other hand, this will be hopefully a bit of a lighter talk maybe from many of you, and it's mainly lagging about how little information we have about what's happening in the deep ocean. So yeah, I'm a postdoc at Scripps Institute of Oceanography, so it's nice actually to be back in the UK after a couple of years, I guess. I did my PhD in Oxford with David Marshall and Helen Johnson, and I'm now working with Sarah Perkey and Jake Gabby in particular, and in collaboration with Bill Smithy as well. So this talk is focusing on the deep ocean circulation and how we can better understand the pathways of dense water masses and their decadal variability from available observations. So I have a bit of introduction, considering that I don't know like how much people know about the deep ocean circulation, but I'll start with a very simple schematic. Because so when I refer to deep ocean circulation, I really mean mostly 2 overturning circulations. And those are sustained by the formation of dense water in the North Atlantic and near Antarctica. And then, as you can see, even if this is a simple schematic, there is like a kind of a system then of interconnected overturning cells. And that those form what we call the global meridional overturning circulation. So this is everything that's happening like below basically the upper ocean wind-driven circulation. So we're talking from like 1,000 meters deep down. And Antarctica here is in the middle, and so you can kind of already see that the Southern Ocean actually plays an important role also in connecting the different water masses across the different basins. But very often we simplify this schematic even more and just look at it in a zonal average sense, so basically average around the globe, and then we end up with this sort of a 2D pictures. And so these are like, I'm just now going to briefly describe the 2 overturning cells I was referring to. And so the first one is actually also what Alberto talked a bit about, consists of like dense water that are formed near Antarctica. So near ice shelves, you have like a densification and then a mixing with the ambient water. And then here is where you form really the densest water that we have in the global ocean. And those like sink all the way basically down to the bottom, and they spread northward in all the ocean basins. And this is really like strongly controlled by topography. And again, linked to what Alberto was describing, this is really where the mixing plays an important role in the regulation of these overturning cells. Because again, we are far from the upper ocean, like in surface processes. So really deep down mixing becomes a key process to bring this dense water up to shallower depth, and then from there they can basically make their way back to the Southern Ocean. And the second overturning cell consists of like the dense waters that are formed in the North Atlantic, so in the Nordic Sea. So we heard as well also about like this processes in our second talk today. So in Nordic Sea is like next to Greenland basically, and then the Labrador Sea, we have again process of densification and the formation of what we call the North Atlantic deep water, which flows like, this is really like, as you can see here, is really like a cell that basically plays a role in the Atlantic Ocean mostly. So it's a characteristic of Atlantic circulation. And this flows then southward at a depth of, well, between roughly 1 and 3 kilometers, all the way until it basically makes its way back to the Southern Ocean, mostly through, this is mostly like an adiabatic flow, so mostly flows along isopycnon with some dipycnon mixing basically in between. And so the point is like, why do we care about this dense ocean circulation? Is because it really plays a key role in climate regulation. So it contributes to the poleward heat transport, and so together with the atmosphere. So in that sense, it contributes to the regulation of the Earth energy balance. And in particular, like in the recent like IPCC report, the last one that came out last year, they really showed that up to 90% of the excess heat that has been put in the atmosphere because of increased carbon dioxide, up to 90% of that excess heat has been taken up by the ocean circulation, well, by the ocean. And so it's carried around through the ocean circulation. And roughly half of that has been taken up in the upper ocean, so in the top 700 meters, and roughly half of the rest of it has been taken up in the deep ocean. And so with actually like an increasing like larger contribution of the deep ocean. And so of course, if you have this excess heat, then that will lead to thermal expansion, and that leads to sea level rise. So roughly half of the sea level rise that we have been observing comes, which is shown here, constituent by constituent, roughly half of it is because of thermal expansion. And so where basically in the water column of this excess heat is going is important to have a better climate prediction. And that is like one also the things that we're still kind of struggling to represent correctly in the climate models. And so when it comes to the deep ocean, we're trying to infer basically how things are changing. So the plot here shows the abyssal warming rates below 4,000 meters. So from the bottom up to 4,000 meters between 1990 and 2019. And so, and this is from available observations, which I will discuss later, are still very sparse in time and in space. But it seems to suggest that there's been significant warming, especially in the southern hemisphere, of the abyssal water masses. But again, these trends have been inferred from the few observations that we have along these black lines, which are like ship-based measurements. So there are huge uncertainties about these trends because these have been sampled maybe like 2 to 3 times in like 50 years. So it's very hard in that sense to infer any trend. And so we are comparing it with different projects that tell us, for example, how much bias we can have. But the point is we're still trying to basically find a way to better understand these trends. And the second thing in terms of why the deep ocean is important in climate regulation is because it plays a key role in carbon storage and sequestration. So I don't think you can actually read much these numbers, but the deep ocean is really like the largest by far, by 2 orders of magnitude, larger carbon reservoir that we have. And so it's where we can store basically large amount of carbons and for long time scale, and long time scale is centennial to millennium. And up to 1/3 of the anthropogenic carbon has been taken up by the ocean. So this is like shows the change in anthropogenic carbon as a column inventory of between 1994 and 2007. So there is a kind of a clear signal of the upper ocean because actually a lot of the anthropogenic carbon has been taken up by the upper ocean. But if we look at like section across the basin, we see that there is also a large amount of carbon ending up in the deep Atlantic Ocean. And that's again because of the North Atlantic deep water that's basically bring it down. And in a recent study, actually, again, I've started finding also increased anthropogenic carbon in abyssal waters. And this is kind of important because that is where it can be stored again for much longer time scale. So it plays a key role in the sense in climate mitigation.
Clarifying question. So what is primary carbon uptake of the ocean?
Yeah, so that is the change in anthropogenic carbon from 1994 to 2007. That's this. So this, well, actually, so this is a kind of weirdly non-periodic thing. So this is the mid-latitudes, that's like the signal of like the upper ocean dry circulation that takes up a part of the carbon. The Atlantic takes up overall a lot more because of the presence of the overturning circulation. So overall, like it takes, I think, almost as much as the Pacific, but it's like half in size. And that's like the key role of the deep ocean circulation, because it brings like, so these are waters that when they take it up when they're in contact with the atmosphere, so when dense water are formed, and then sequestered deep down. The abyssal waters have not taken up so far as much, but there are recent studies that show that especially in the Indo-Pacific basin, that is also in fact increasing. And that's also like, depends of course also how dense waters are formed.
Why not southern?
When the Southern Ocean, most of it is taken up around 50 south, which is also where dense waters are formed. So some of the abyssal waters are formed very close to Antarctica near ice shelves. But then as they sink down, they really mix also with some of the ambient water. And most of it then northward export happens around this latitude of, which is where when you see that red patches as well. So that's also where, if you look at the mixed layer depth that Matthew was showing, that's also where it is the deepest in winter. So it's a signal also like of dense water downwelling in those locations. But in the very deep is still like a present happening. That also, I guess I haven't looked at too much yet, but in terms of also the presence of the sea ice also plays in that sense a key role in terms of where when the carbon can be sequestered. And okay, the problem is that when it comes to the deep ocean outreach, we do not have a lot of observations yet. So to give a sense of how little observations we have, the panel here shows the observational coverage as in terms of a percent about how much of the ocean we are sampling for different depth ranges up to 1800 meters for temperature. So this means that if you look at the dark blue line in the northern hemisphere, we have roughly up to 50% of the ocean sampling coverage for temperature again. And in the southern hemisphere, we only have really to up to 20%. And this is for temperature, which is one of the most well-observed variables, and in the upper ocean. So as we go deep down, basically, we really have like 5 to 10% of the ocean being south, but in some places, probably even like in the southern hemisphere, even less. And so when we really try to basically understand how the deep ocean circulation works and how variable it is, we still mostly rely on ship-based measurement. These are the lines here show the hydrographic sections, so where we go with the ships to take measurements. These are not all the lines, there are a few more, but these are the main ones that are like maintained by international observational programs. The color represents a number of occupations, and this is a number of occupations from the 80s up to now. So when we're lucky, basically like in the Atlantic Ocean, especially, we have maybe 5 or 6 occupations, so one every decade. In other places, we have less than that. And so this is really just to stress a point that we really don't have much observations. We're talking sometimes about 1 or so maybe 2 to 3 occupations in 50 years. So it's really, I mean, we're kind of struggling in the sense when we really want to discuss like the time variability of the deep ocean circulation. And so what I'm doing, yeah. Mm-hmm.
In the upper ocean, does it include Argo?
This includes Argo, yeah, but Argo floats, so those are autonomous floats that have like a 10-day cycle, but they still spend the most of the time at 1,000 meters, 9 of the 10 days, and then they go down to 2,000 meters and come back up. So there is a big gap in the sense that when you go down below like 1,000 meters. And this is Argo.
I still don't understand because they park at 1,000 meters, they go down and then they go up.
Yeah.
But they don't preferentially spend more time up than down. So why? And that is the Argo range, 2,000 meters. So why does it drop? I mean, not all of Argo flows.
No. that's one thing. Well, need to check in that sense. This is. It has this is the core of it is XVT. This which is up, yeah, and then I don't think it makes sense that Argo change much that picture. Yeah. No, thanks. So yeah, so what I'm doing now is basically to try to find ways to start at least addressing the fact that the observations are very sparse in time. And basically come up with ways so that we can produce an annual picture of some of the tracers, and I will discuss in a second what tracers I'm talking about, along these hydrographic sections. And then the next part of the problem would be trying to, of course, solve for the spatial sparsity, because each of these lines are a few thousands of kilometers apart. So I will discuss the method in a second, but in general, like every time when we are trying to infer properties, like in tracers, for example, like in the ocean interior, which you just see here, I hope you can see it is quite low. If we know the surface boundary condition of this property, we see as here, we can propagate that information in the interior with what we call like the Green's function boundary propagator. That is also known as the age spectrum or transit time distribution. And what it actually is the probability density function of transit times defining the water age at that location in the interior. So I actually have a figure here that helps in the sense of, so take one of the sections I was showing you before and take one point in the ocean interior. And the properties there will be given by the different water parcels that reach that point, which could have followed different paths, and so have a different transit time to reach that location. And the Green's function gives you the distribution of the transit time, and so connects the surface information, if we know what the surface boundary conditions are, with that location in the ocean interior. So what we want to do in general is to solve for these Green's functions so that we can then reconstruct tracer properties in the interior of the ocean. So how do we do that? First, we need to know what the surface boundary conditions are. And so now it's like, okay, what the tracer I'm talking about? I'm talking about specifically for the method that we apply, that we use here, about three different tracers. Two of them are what we are chlorofluorocarbons, or CFCs for short, and one is a sulfur hexafluoride, or SF6. The panel here shows their atmospheric history, so how they have been increasing in the atmosphere. So how their concentration has been changing in the atmosphere. So these are all anthropogenic tracers in the sense that they've been produced and were used like in industrial like production, like in your AC system, for example, and so on. So they are inert in the ocean. So they're soluble, they're taken up again when less waters are formed, but they do not react with biology or other processes. So in that sense, they're a perfect tool. Their concentration has been increasing from like the 40s, 50s, almost linearly. For SF6, they're still going up. For CFCs, their concentration in the atmosphere started decreasing in the late 90s, early 2000s, because they do interact with the ozone in the stratosphere, and so they damage the ozone layer. And so there's been a Montreal protocol that decided to ban or at least reduce their usage to limit that damage to the ozone layer. So this is why their concentration now is decreasing. And we use these traces because, again, they are inert, but also because of their time-variant atmospheric history. They can tag the dense waters when these are formed. And so they're the perfect tool in the sense to trace where dense waters are, because these tracers do not exist in the sense in the ocean. So we kind of have a clear signal of where they're going. And so we have this, sorry, and just last thing, like this is the atmospheric history. We know then that what their solubility in the seawater is and how that varies depending on temperature and salinity. And we can, we make some assumption, and I'm not going into the details about that in terms of what's their saturation in seawater, but so we can then from this infer the surface boundary conditions at the surface of the ocean. And then if we know the surface boundary condition, then we can use information of the observed tracers. So these tracers have been observed occasionally along the hydrographic section. You have an example here. So this is the number of occupations of CSC11 in the ocean below 1,000 meters. So you can see there are more of these are more of the lines of what I showed before, because again, those were just the one maintained by international programs. But you can also see that most of the time we really have only one occupation and occasionally 2 or 3. So these are not sampled as frequently as other properties. But point being, so we have some of observations. So we know what the tracer concentration is in the interior. We know the surface boundary conditions, so we can invert to find the Green's function. And how do we do that? Is that we really, the method that we use here is just a modified least square problem. So we solve for the Green's function that minimizes the discrepancy between the predicted tracer concentration and the observed one, and between the a first guess of Green's function. Again, I'm not going into the details now, but we give it basically just a first guess. The two things have different weights, so it's a weighted least square problem. We really tend to, of course, like focus on minimizing this discrepancy. So overall, it's a very much underdetermined problem, because very often we have only like one, or when we are lucky, like maybe 4 or 5 occupations along, again, 5 decades. So I'm just going to run you through a quick example in terms of how does this method exactly work. And this is just with synthetic data, so it's still not applied to the actual observations. So start by assuming that we actually know what the Green's function is. And so this is like, imagine like in a location in the ocean interior, and this is again the PDF of the transit times. So the times that particles basically took to arrive into that whatever random location. And we know the surface boundary condition of the tracers, so we can reconstruct their concentration at that location. But again, in reality, we don't know what the truth, like what's the true tracer concentration. What we have is maybe one year we sampled it, and this is an example. It was like, okay, let's assume we have one occupation one observation of CSC11 and CSC12 in 1995. So we are subsampling and adding some error.
How did you get the
So this is taken. So this is an inverse Gaussian, and it's like assuming that it. I assume it in this example. In the actual method, when I apply to the data, the first guess is an inverse Gaussian, but is not too constrained to have that parametric form, because we actually know that in the ocean, this is actually true in many places, that this is a good representation of what like the transit time distribution should look like. But in some places you can have a bimodal, for example, solutions, because you have waters of different origins with different ages kind of coming together, and depending on the locations, you can have also multiple modes. But
you have different timeline dependencies in different locations.
You can have, yeah. Yeah, so we tried a different prior, for example, and the solution is, it can be sensitive to the prior like assumption of the of the Green's function that we give into the method. So this is why in the cost function of the least square problem, most of the weight is given to fit the data first, and without constraining it too much to any parametric form. But in this example, we just, yeah, we go with an assumption. And so, yeah, so I assume you have then only one occupation again in 1995. And so this is what I'm saying, like then also in terms of the Green's, the first guess. So we have this information, we know the surface boundary condition. We assume this is the dashed line is our initial first guess, and I didn't really go into any details in terms of like how we decided that that's our first guess. We can talk about it later if anyone is interested, the technicalities. And then we solve for the Green's function, and this is the solution that we find with like a dash and dotted line. And once we have that, we can then reconstruct the.
So you didn't recover the true one?
Not completely, no. But it's already pretty good for what we know, considering we have only one occupation. And this is the actual prediction, and the error bar is one standard deviation, and again, depending on the weight associated with the first guess, the error bars can be different. So we kind of fit the data perfectly, let's say, when we have observation, because that's really the only constraint we have. And then as we move further away in time from the data that we have, our prediction can be more or less good, depending on how many observations also we have. In locations where we have 2 or more occupations, of course, the solution improves. But most of the time, at least I know that as we did, like we have been trying at least to make sure that that the truth is within the error bars or our estimate. And so this is again was an example with synthetic data. Okay, so now it's really jumping to, okay, we apply then to the actual data, so along all the different sections. And this is showing an example of the time corrected CFC 11 in 2020 in the Atlantic Ocean. So I'm not sure you can see it here, but this is a section that really basically spans the middle of the Atlantic Ocean from the North Atlantic all the way to the Southern Ocean, which is here. And just so again, this is just totally reconstructed. We didn't know anything about what the concentration were in that year. And the last time this was actually sampled was in 2013. Okay, so I'm just going to really quickly guide you basically through what are the main patterns that we see and along this section. And so starting from from the Southern Ocean and then moving north. So here, for example, you see that so this is really, sorry, this part here up to roughly 60 south is we are in the Weddell Gyre. So we are here like in Antarctica, and here is where we have dense water coming from the east and looping around the gyre, and coming out at the bottom has newly formed abyssal waters, and which is, so as they are formed, this is where they are in contact with the atmosphere, and that's why we have, for example, this signal of enhanced CFC 11 and in the bottom here. In the middle of the gyre, on the other hand, we have like the minimum, which is again consistent with this gyre circulation. Then this is basically the contours here, and like the fact that we have a higher concentration near the bottom. Again, that's like the northward spreading of abyssal waters that is captured by the reconstruction, and all the way basically almost up to the equator. And sorry, I forgot to say, but this is like picomole per kilo, and we have a detection limit, and which is like 0.01 picomole per kilo. So basically, CFC 11 now are above the detection limit everywhere in the Atlantic, apart from a few patches, basically in the eastern flank of Atlantic. Then when we move to the equator,
So the CFC started going into the ocean in
1950, yeah.
So like in 70 years, they're all over the ocean in all depths?
Almost, well, not at all depths, but well, the Atlantic Ocean, yes, but like in the Pacific, no, not really. They are, I have a plot of where they are in the, at the bottom of the ocean. But in the Pacific and Indian Ocean especially, you have a high CFC associated with like intermediate waters. So in that sense, the picture for upper ocean is similar in those two basins. And you see the signal of Antarctic bottom water spreading. But there is no North Atlantic deep water. Well, there is no like a dense water coming from the north, right? So in that sense, the interior is still lacking. There are still no CFCs in the interior of those two basins.
So this is connected to Paolo's question about carbon uptake. You know, in that Atlantic happens much more efficiently.
Yes, yeah, exactly. And so, yeah, so, and actually exactly, so for example, all of this recirculation so all of this sort of a signal that we see at the equator in the Atlantic, that's again, because we have dense waters coming from the North Atlantic. So here you see that there is a sort of a maximum of CFCs. These are density surfaces. Sorry, yeah, two density boundaries if you want. So this is like the yellow line indicate the density levels. And then we have a sort of a minimum in between and again, a maximum below. And this pattern is associated with the, again, dense waters coming from the North Atlantic, but they're usually in fact split in what we call like the upper North Atlantic deep waters, then we have the middle North Atlantic deep waters and the lower North Atlantic deep waters. And so what we know is that as this water, dense waters flow southward, once they reach the equator, part of them recirculates eastward, which is shown in the schematic here. And so what we are seeing here is really a section across that recirculation. So basically these waters are coming, if you want, towards you. But then we are and this is actually still like people are still trying to understand exactly the details of these dynamics, because when a part of those dense waters recirculate from the east and they move further west, and this is why we have this minimum, because this is the signal that is somewhat diluted from older waters. And this pattern is consistent with other tracers. So the plot here is oxygen. Again, you have a maximum, a minimum, and a maximum. And then the lower maximum is the signal is a mixed signal of the North Atlantic deep waters and the arrival also of abyssal waters. And I mean, the nice things for us is like, okay, our method doesn't know anything about this circulation or about the density classes, and it still catches like the patterns at the right densities compared also with other tracers and other properties. And then, yeah, the largest like concentration here again are associated with the sulfur flow of North Atlantic deep waters. And so to go back actually to your questions in terms of where do we find the CFCs right now after like 70-ish years. This shows the arrival time of CFC 11 at the ocean bottom. So arrival time means the first time that our reconstruction finds values that are above the detection limit. And so everything that is in red is basically places where we have not detected them yet, again, at the ocean floor. So it shows where, I don't know if you can see it very well, but it actually really shows like darker blue should be like where you have dense waters formation. So in the North Atlantic, in the Weddell Sea, in the Ross Sea, this is the Adelie Coast, and this Adelie Coast, Ross Sea, and the Weddell Sea are the three key regions where abyssal waters are formed. And then you can sort of like, you can see the northward like pathways of abyssal waters, the southward pathway on North Atlantic deep waters. And you can see how then abyssal water are spreading northward in all the basins. We see them all the way going to basically also the North Pacific. And we see them like crossing key passages. So this is the Southampton passage. And that's like, if you look at the mean age of waters in those locations, that's usually much larger. But so that's again, like it's a PDF of the transit times. And we already see like in 70 years, they actually already reached those locations. And this is, again, limited, of course, like to the last 70 years in this, because these tracers were not present before. So yeah, I'm also done, thanks. So the last thing that we can do actually with this reconstruction is also start looking into the decadal variability. Because one thing actually I haven't mentioned yet is that our reconstruction assumes a time in circulation. So when we compare our reconstruction with the observed concentration, if there is a discrepancy, we'll start looking into whether that is explained because the time in mean circulation does not explain the reconstructed tracer concentration, which then will mean that there have been changes in the formation rates of the water masses. And this is what is shown here. So I forgot to add a plot of where this section is, but this is a section in the South Pacific, which is, sorry, it's just here. It's in front of the Ross Gyre. So where abyssal waters are formed. And what this plot shows is the difference between our reconstructed CFC11 concentration and the observed one. So you can see that consistently and it increases with time, our reconstruction shows like a higher CFC concentration than what we have observed. So the time in a circulation that our method assumed was stronger than the actual circulations. And so suggests that there has just been like a slowdown in the formation rates of abyssal waters. And that again connects with the plot I showed early on in terms of is there are abyssal waters warming, because if there is a slowdown, that signal will transfer into a warming signal. So in that sense, confirms the trends inferred from observations. And just to make a point that this is not something we see only along one section, these are other sections in the Indian Ocean. Again, so this is abyssal waters that have been formed next to the Ross Sea and the Delhi coast, and they're flowing northward. And you can see that as time passes, we see the same signal of kind of slowing down. And this is still really very much kind of work in progress, in the sense with, of course, we need to check not just like the difference, but also the uncertainty of our estimate, and look at things a bit more carefully. But it seems like to point out to kind of a decline again of abyssal water formations. And so just to conclude, so the point is like, yeah, deep ocean observations are sparse in space and time, but we can start like using a bit of a data-driven method. Well, not start, I guess, but there are like different ways to use data-driven method to start digging into what are the timing pathways, but also the decadal variability. One thing is that once we also solve for this, we will need to do some objective mapping or interpolation then to also fill for the spatial sparsity of the data. But once we do that, we can also look at the tracer inventories and calculate formation rates of the different water masses. Having the Green's function means also that we can propagate other properties and not just the tracer that we have used. Once we have a Green's function, we can propagate anthropogenic carbon, we could propagate sea surface temperature anomalies, and so have an idea of the excess heat. And so build like a bit more of a picture again of how things are changing in the deep ocean. And I mean, this is our like kind of work in progress in terms of also using this, for example, to compare it with other measurements to infer also the cross density mixing that Alberto, for example, has been talking about. And I think I'm done. Thank you.
That's one question. Can you expand on the last point?
Also, this one?
If you go one slide back for joining any, if you go just one slide back, can you make a connection between what Alberto was talking about? Like in terms of, well, you made the point at the very end of this talk that the deep ocean can be leakier than we think. So does it have anything to do with the Atlantic filling up with tracers so rapidly? We tend to think of deep circulation to be on centennial time scale and abyssal to be on millennial time scale. So something filling up the whole ocean in 50 years.
Yeah. And I mean, I think for the Atlantic in that sense it was even a bit less of a surprise, but for sure, like when it comes to the Indian and the Pacific, they definitely spread around the whole globe at faster timescales than what we expected. So yeah, I actually think maybe we can try to use this project, since it has under resolution, maybe to look into the rates of upwelling and what we think they should be and what they actually are from tracers, to see if that like kind of answers Alberto's point. I mean, nobody thought that the mean, like when we say like the interior of the Pacific, we say there's a mean age of some thousands of years, like 1500 maybe. And that's again the mean age, and there is a time distribution, but so we are probably on the like in the sense lower end of like the youngest water that are there, but they're still like, I guess, like much younger than what we expected. But
yeah, I want to make a point, which I think is subtle, which is what Alberto was talking about. So I'm filling in for that for Alberto. But if classically we would think that you have internal mixing, diapictal mixing that broadly upwells stuff in the interior of the ocean. And so for a tracer to make it to the deep ocean, you would have to sink at high latitudes. But if what Alberto was saying is correct, in that when you have topographic induced bottom and has mixing, that's going to lead to downwelling. So once you get these tracer to the base of the mid-latitude wind-driven gyres, then you can actually start pumping them down, and they can hit the topography and shoot up along topography. You basically get a dipole mechanism that can steer it in the interior much more efficiently. And if that paradigm is correct, which is why they're doing that experiment, then a tracer would mix in a whole basin where you have rough topography much faster than we classically thought. So I think you're showing that that is the case.
Right.
So in that case, I think this will come together really nice.
From the way to take into this more. And actually, sorry, but just one last minute. I mean, it's just to appreciate in that sense is like how difficult it is from observation. This was the last time that this tracer are being used to be a bit more of a global picture in terms of spreading, and this was in the 90s, so they didn't really make it that far, and that was hand contour, which, okay, to be fair, they knew a lot about the circulation, but we still had so little observations that we just basically went hand contour where they data fitted. So in that sense, yes, hopefully the picture now is a bit more global as well. Okay. And thanks to the organizer, and others.
Great. So that brings the talks to a close today. So before we go into barbecue, I'd like to just place on record our thanks to the CDT for making today possible, as well as to Barsha for being so efficient with all of the organization. And once again, to all of our speakers for giving us such a fantastic set of talks for today. So let's have another round of applause for our speakers. So for those of you who are registered, the barbecue is at 170 Queensgate Terrace. So if you could make your way there, that's